Good evening. It is good to have you with us here on Quiet Between the Stars. Tonight, we begin something rather extraordinary. We are going to leave Earth behind and travel outward, far beyond anything our ancestors could have imagined. Not in a spacecraft, but in understanding. We will cross distances so vast that light itself, traveling at 300,000 kilometers every second, takes millions upon millions of years to make the same journey. Consider this. If you could somehow travel at the speed of light, you could circle our entire planet 7.5 times in a single second. Yet even at that impossible velocity, reaching the nearest star to our Sun would still take you over 4 years. And that star, Proxima Centauri, is practically our next-door neighbor. The universe stretches so much further than that, so incomprehensibly further. Over the course of this journey, we will begin here, in the spiral arms of our own Milky Way galaxy, where our solar system drifts through a quiet region called the Orion Spur. From there, we will travel past the supermassive black hole at our galaxy's heart, out through the local group of galaxies, past great clusters and superclusters, until we reach the largest known structures in existence, and then beyond them, into the cosmic voids. Those immense dark spaces between the filaments of matter where almost nothing exists at all. If you enjoy Quiet Between the Stars, please take a moment to subscribe. It helps others find these journeys, and it means a great deal. Now then, let us dim the lights, let the day fall away, and let us begin. 4.5 billion years ago, the Earth did not exist as we know it. There was no blue marble suspended in the darkness of space, no continents, no oceans, no whisper of wind across any surface. Instead, there was a sphere of molten rock, glowing with the fierce orange and red of temperatures exceeding 2,000 degrees Celsius. This was the magma ocean, a global sea of liquid silicate that covered the entire planet to depths of hundreds of kilometers. The heat that created this inferno came from 3 sources, each contributing to the extraordinary temperatures that kept the young Earth in a molten state. First, there was the energy of accretion itself. As countless planetesimals and smaller bodies collided with the growing proto-Earth, their kinetic energy converted directly into thermal energy upon impact. Each collision was like striking a match, except these matches were asteroids tens of kilometers across, and their impacts released energy equivalent to billions of nuclear weapons detonating simultaneously. Second, radioactive elements were far more abundant in the early solar system than they are today. Aluminum-26, with its half-life of only 717,000 years, decayed rapidly within the first few million years, releasing tremendous heat into the planet's interior. Potassium-40, uranium-238, uranium-235, and thorium-232 added their own contributions, their atomic nuclei splitting apart and releasing energy with each decay event. The concentration of these radioactive isotopes was perhaps 3 to 4 times higher than it is in the modern Earth, meaning the planet generated heat internally at a rate far exceeding what we measure today. Third, and perhaps most dramatically, came the moon-forming impact. Approximately 4.5 billion years ago, a Mars-sized body called Theia struck the proto-Earth at an oblique angle. The collision was so violent that it vaporized significant portions of both bodies, ejecting debris into orbit that would eventually coalesce into our moon. The energy released in this single event was sufficient to melt the entire Earth down to its core, resetting any cooling that might have begun and ensuring that the magma ocean would persist for millions of years longer. In this molten state, the Earth began a process of differentiation. Iron and nickel, being denser than the silicate minerals surrounding them, sank toward the center of the planet. Droplets of liquid metal, each perhaps a few centimeters across, fell through the magma like rain falling through air, except this rain moved through rock at temperatures where the distinction between solid and liquid became meaningless. Over a period of perhaps 30 to 50 million years, this iron rain accumulated at the center of the Earth, forming the metallic core that persists to this day. The core's formation released additional gravitational energy, enough to raise the temperature of the entire planet by another 1,500 degrees Celsius. Meanwhile, at the surface, the magma ocean radiated its heat into space. The rate of cooling depended on the temperature difference between the surface and the cold vacuum above, and on the presence or absence of an atmosphere. Early in Earth's history, a thick atmosphere of vaporized rock and metal may have acted as an insulating blanket, slowing the rate of heat loss. Steam and carbon dioxide, released from the magma itself, added to this primordial atmosphere, creating a greenhouse effect that kept surface temperatures elevated. But even with this insulation, the laws of thermodynamics demanded that heat flow from hot to cold. The surface of the magma ocean, exposed to space, cooled first. As temperatures dropped below approximately 1,200 degrees Celsius, the first minerals began to crystallize. Olivine, a magnesium-iron silicate with a melting point around 1,900 degrees Celsius, was among the earliest to form. These crystals were denser than the surrounding liquid, and they sank, drifting downward through the magma like snowflakes falling through water, accumulating at the base of the magma ocean in layers that would eventually become part of the mantle. The cooling was not uniform. Convection currents stirred the magma ocean, carrying hot material from the depths to the surface and returning cooled material to the interior. These currents moved at speeds of perhaps a few meters per second, fast enough to keep the magma well mixed, but slow enough that the process of crystallization could proceed in an orderly fashion. The pattern of convection may have resembled the surface of a pot of thick soup on a stove, with broad upwellings and narrow downwellings creating a constantly shifting mosaic of hotter and cooler regions. As millions of years passed, the magma ocean continued to lose heat. The rate of cooling slowed as the temperature difference between the surface and space decreased, but it never stopped entirely. Computer models suggest that the transition from a fully molten surface to a solid crust may have taken anywhere from 1 million to 100 million years, depending on the thickness of the early atmosphere and the rate of heat production from radioactive decay. The first solid crust was nothing like the continents we know today. It was thin, perhaps only a few kilometers thick, and composed primarily of basalt, a dark volcanic rock rich in iron and magnesium. This crust was unstable, constantly being recycled back into the magma ocean as new material erupted from below. Imagine a skin forming on the surface of cooling lava, only to be broken apart and remelted moments later. This process repeated countless times, each cycle allowing the planet to lose a little more heat, each cycle bringing the surface temperature a few degrees closer to the point where water could exist as a liquid. The transition from magma ocean to solid crust marked a fundamental change in Earth's evolution. With a solid surface, the planet could begin to retain an atmosphere in a more stable configuration. Volcanic gases, released from the cooling interior, accumulated above the surface rather than being immediately reabsorbed into the molten rock. Water vapor, carbon dioxide, nitrogen, and sulfur compounds built up over millions of years, creating the conditions that would eventually allow for the formation of oceans. The heat that remained trapped within the Earth did not simply disappear. It became the engine that would drive plate tectonics, volcanism, and mountain building for billions of years to come. Even today, 4.5 billion years after the planet's formation, the Earth's interior remains hot enough to melt rock, with temperatures at the core mantle boundary reaching approximately 4,000 degrees Celsius. The planet continues to cool, losing heat at a rate of about 47 terawatts. But at this pace, it will take many more billions of years before the interior solidifies completely. In those early days, as the first permanent crust began to form, the Earth was a world of extremes. The surface temperature, even after the magma ocean had largely solidified, remained above 200 degrees Celsius for millions of years. The atmosphere was thick with carbon dioxide and water vapor, creating a greenhouse effect that trapped heat and kept the surface inhospitable by modern standards. Meteorite impacts continued, though less frequently than during the main phase of accretion, each one delivering additional energy and occasionally remelting portions of the newly formed crust. Yet within this hostile environment, the foundations of everything that would follow were being laid. The separation of core from mantle established the density structure that would govern the planet's behavior for eons. The formation of the first crust created a boundary between the interior and exterior, a surface upon which future processes could act. The accumulation of an atmosphere provided the raw materials for weather, climate, and eventually, the chemistry of life. The cooling of the early Earth was not an event, but a process, one that unfolded over timescales almost impossible for the human mind to grasp. 1,000,000 years is 1,000 millennia, 1,000 times longer than the entire span of recorded human history. And the cooling of the magma ocean took tens of millions of years, perhaps 100 million, each year bringing changes so subtle that no observer, had one existed, could have detected them. Yet the cumulative effect of all those years was the transformation of a ball of molten rock into a world with a solid surface, an atmosphere, and the potential for oceans. The stage was being set, slowly and patiently, for everything that would come next. As the crust thickened and the surface temperatures dropped below 1,000 degrees Celsius, something remarkable began to happen at the atomic level. The chaos of the molten rock, where atoms tumbled freely in a disordered sea of liquid silicate, began to give way to order. Atoms, once jostling without pattern, started to find their places. locking into repeating geometric arrangements that would become the first minerals of the young Earth. This process, crystallization, is governed by the fundamental laws of thermodynamics. When a liquid cools, its atoms lose kinetic energy. They slow down, and as they slow, the attractive forces between them, the electromagnetic interactions that bind atoms together, begin to dominate over the random thermal motion that kept them apart. At a critical temperature, specific to each chemical composition, the atoms snap into fixed positions relative to one another, forming a crystal lattice. This lattice is not arbitrary. It is the lowest energy configuration available to those particular atoms under those particular conditions. A geometric solution to the problem of minimizing energy while maximizing stability. The first minerals to crystallize from the cooling magma ocean were the refractory ones, those with the highest melting points. Among the earliest were the olivines, silicate minerals rich in magnesium and iron. Olivine crystallizes at temperatures around 1,200 to 1,900 degrees Celsius, depending on its exact composition. Its crystal structure is orthorhombic, meaning its atoms arrange themselves in a pattern defined by 3 unequal axes meeting at right angles. Each silicon atom sits at the center of a tetrahedron of 4 oxygen atoms, and these tetrahedra are linked together by magnesium or iron ions. The result is a dense, hard mineral, typically green in color when rich in magnesium, that would have formed tiny crystals suspended in the still molten rock, slowly sinking or rising depending on their density relative to the surrounding liquid. As the temperature continued to fall, other minerals joined the olivine. Pyroxenes, another family of silicates, began to crystallize at temperatures between 1,000 and 1,400 degrees Celsius. Their structure is different from olivine, built from chains of silicon-oxygen tetrahedra rather than isolated units. These chains give pyroxenes their characteristic elongated crystal habit, their tendency to form prismatic shapes. Augite, a common pyroxene, contains calcium, magnesium, iron, and aluminum in addition to silicon and oxygen, a complex recipe that reflects the diverse chemistry of the early magma ocean. The sequence in which minerals crystallize from a cooling melt is not random. It follows a predictable order first described by the geologist Norman Bowen in the early 20th century. Bowen's reaction series, as it is called, arranges minerals according to their crystallization temperatures. At the top are the high-temperature minerals like olivine and calcium-rich plagioclase feldspar. As the melt cools, these early crystals react with the remaining liquid, transforming into new minerals or being joined by others. Pyroxenes give way to amphiboles, which give way to biotite mica. On the feldspar side, calcium-rich varieties are replaced by sodium-rich ones. At the bottom of the series, at temperatures below 700 degrees Celsius, quartz finally crystallizes, the last major mineral to form from a silicate melt. This sequence played out across the cooling Earth over millions of years. The magma ocean was not uniform. Convection currents stirred it, bringing hotter material up from the depths and cooler material down. Crystals that formed near the surface might be carried downward, remelted, and reformed. Others might accumulate, sinking to the bottom of the magma ocean to form the earliest layers of what would become the mantle. The process was dynamic, a slow churning that sorted the elements of the Earth according to their chemical affinities and the physical properties of the minerals they formed. Consider the scale of time involved. A single crystal of olivine might grow at a rate of a few micrometers per year under the conditions of the cooling magma ocean. A crystal 1 centimeter across would take thousands of years to form, and the magma ocean contained countless such crystals, each growing at its own pace, each contributing to the gradual transformation of liquid rock into solid. The process was imperceptibly slow by human standards, yet relentless. Year after year, century after century, the proportion of solid to liquid increased. The geometry of crystal lattices is a direct expression of atomic forces. In a crystal of quartz, each silicon atom is bonded to 4 oxygen atoms arranged at the corners of a tetrahedron, and each oxygen atom is shared between 2 silicon atoms. This creates a 3-dimensional network of extraordinary strength and stability. The angle between the silicon-oxygen bonds is approximately 144 degrees, a value determined by the quantum mechanical properties of the electron orbitals involved. The result is a mineral with a hardness of 7 on the Mohs scale, resistant to weathering and nearly insoluble in water. Quartz crystals can persist for billions of years, and some of the oldest minerals ever found on Earth are tiny grains of zircon, a zirconium silicate, that have survived since the Hadean Eon, more than 4 billion years ago. Zircon is particularly important to geologists because it incorporates trace amounts of uranium into its crystal structure when it forms. Uranium-238, one of the isotopes present, is radioactive. It decays into lead-206 with a half-life of 4.468 billion years. By measuring the ratio of uranium to lead in a zircon crystal, scientists can calculate how long ago that crystal formed. The oldest zircons yet discovered, found in the Jack Hills of Western Australia, yield ages of up to 4.4 billion years. These tiny crystals, some no larger than a grain of sand, are windows into the earliest history of the solid Earth, survivors from an era when the planet was still largely molten. The formation of minerals was not limited to silicates. As the Earth cooled and differentiated, other chemical compounds found their stable forms. Iron and nickel, being dense metals, sank toward the center of the planet, eventually forming the core. But some iron remained in the mantle and crust, combining with sulfur to form iron sulfides like pyrite and pyrrhotite, or with oxygen to form magnetite and hematite. These iron oxides would later play a crucial role in the history of life. But in the Hadean Eon, they were simply part of the growing inventory of solid minerals. The process of crystallization also released heat. When atoms transition from the disordered state of a liquid to the ordered state of a solid, they release the latent heat of fusion. For silicate minerals, this amounts to several hundred kilojoules per kilogram. This released heat slowed the cooling of the magma ocean, extending the process over additional millions of years. The Earth was not simply radiating heat into space, it was also generating heat internally through crystallization, radioactive decay, and the ongoing settling of dense materials toward the core. By approximately 4.4 billion years ago, the surface of the Earth had cooled enough for a stable crust to form. This crust was thin, perhaps only a few kilometers thick in places, and it was constantly being disrupted by volcanic activity and the churning of the mantle below. But it was solid, a platform of crystalline rock floating on the denser, still partially molten interior. The minerals that composed this early crust were predominantly mafic, rich in magnesium and iron, similar to the basalts that erupt from oceanic volcanoes today. Lighter, more silica-rich minerals like quartz and feldspar would come later, as the crust evolved and differentiated through repeated cycles of melting, crystallization, and remelting. The crystal lattices that formed during this era were the first permanent structures on Earth. They were archives of the conditions under which they formed, their compositions and structures recording the temperatures, pressures, and chemical environments of the early planet. Each mineral was a frozen moment in the slow cooling of a world, a testament to the patient work of atomic forces arranging matter into order. And as the crust thickened and stabilized, these minerals would become the foundation for everything that followed: the continents, the mountains, the sediments, and eventually the rocks that would preserve the first traces of life. The crust that had formed from those first crystallizing minerals was not a single unbroken shell. It was fractured, mobile, floating on a layer of rock so hot that it behaved almost like a fluid over geological timescales. This was the beginning of plate tectonics, the great engine that would reshape the surface of the Earth continuously for billions of years, building mountains and tearing continents apart, opening oceans and closing them again in cycles that span hundreds of millions of years. To understand why the Earth's surface moves, one must look beneath it, into the mantle. This layer of rock extends from the base of the crust down to a depth of nearly 2,900 kilometers, where it meets the liquid iron outer core. The mantle is not molten in the way most people imagine. It is solid rock, primarily composed of silicate minerals rich in magnesium and iron, such as olivine and pyroxene. But at the temperatures and pressures found in the deep Earth, between 1,000 and 3,700 degrees Celsius, this solid rock can flow. Not like water, not even like honey, but over millions of years, it deforms and moves like an impossibly slow river of stone. The driving force behind this movement is heat. The Earth's interior is hot for two reasons. First, there is primordial heat, the thermal energy left over from the planet's formation, from all those collisions and compressions that built the world from dust and planetesimals. Second, and perhaps more importantly over geological time, there is radiogenic heat, the energy released by the decay of radioactive isotopes within the mantle and crust. Uranium-238, with its half-life of 4.5 billion years, thorium-232 at 14 billion years, and potassium-40 at 1.25 billion years, all contribute to this internal furnace. As these atoms decay, they release energy, keeping the Earth's interior warm enough to drive the convection currents that move the plates. Convection is a simple principle made complex by the scale and materials involved. When rock in the lower mantle is heated by the core and by radioactive decay, it becomes slightly less dense. This hotter, less dense rock rises slowly toward the surface, a journey that takes tens of millions of years to complete. As it rises, it cools, becomes denser, and eventually sinks back down toward the core, where it is heated again. This creates circulation cells within the mantle, vast loops of slowly churning rock that transfer heat from the interior to the surface. The speed of this movement is measured in centimeters per year, roughly the rate at which human fingernails grow. Yet over hundreds of millions of years, these centimeters accumulate into thousands of kilometers. The lithosphere, the rigid outer layer of the Earth that includes the crust and the uppermost mantle, is broken into a mosaic of plates. There are 7 major plates and numerous smaller ones, each moving independently, pushed and pulled by the convection currents below and by forces at their edges. The Pacific Plate, the largest, covers an area of roughly 103 million square kilometers. The North American Plate, the Eurasian Plate, the African Plate, the Antarctic Plate, the Indo-Australian Plate, and the South American Plate make up most of the remaining surface. Smaller plates, like the Nazca Plate off the western coast of South America or the Philippine Sea Plate, play crucial roles in regional geology despite their smaller size. Where plates meet, 3 types of boundaries form, each with distinct geological consequences. At divergent boundaries, plates move apart from each other. The most prominent example is the Mid-Atlantic Ridge, a submarine mountain range that runs down the center of the Atlantic Ocean for over 16,000 kilometers. Here, the North American Plate and the Eurasian Plate are separating at a rate of about 2.5 centimeters per year. As they pull apart, hot mantle rock rises to fill the gap, melting as the pressure decreases and creating new oceanic crust. This process, called seafloor spreading, has been widening the Atlantic Ocean since the breakup of the supercontinent Pangaea, which began approximately 200 million years ago. Iceland sits directly on the Mid-Atlantic Ridge, one of the few places where this underwater mountain range rises above sea level, allowing geologists to study the process of crustal creation directly. At convergent boundaries, plates collide. The outcome depends on the types of crust involved. When oceanic crust meets continental crust, the denser oceanic plate subducts, diving beneath the lighter continental plate and descending into the mantle. This process creates deep ocean trenches, like the Mariana Trench in the Western Pacific, which reaches a depth of nearly 11,000 meters below sea level. As the subducting plate descends, it carries water and sediments into the mantle. At depths of around 100 kilometers, the increasing temperature and pressure release this water, which lowers the melting point of the surrounding mantle rock, generating magma. This magma rises to feed volcanic arcs, chains of volcanoes that parallel the trench. The Andes Mountains of South America and the Cascade Range of the Pacific Northwest are examples of such volcanic arcs, built over millions of years by the subduction of oceanic plates beneath continental margins. When 2 continental plates collide, neither can easily subduct because both are too buoyant. Instead, the crust crumples and thickens, building massive mountain ranges. The Himalayas are the most dramatic example, formed by the ongoing collision between the Indian Plate and the Eurasian Plate. This collision began approximately 50 million years ago, when the Indian subcontinent, which had been drifting northward across the Tethys Ocean at a rate of about 15 centimeters per year, finally made contact with Asia. The collision has not stopped. India continues to push into Eurasia at roughly 5 centimeters per year, and the Himalayas continue to rise by about 5 millimeters annually. Mount Everest, at 8,849 meters, is still growing, though erosion works to counteract this uplift. The third type of boundary is the transform boundary, where plates slide past each other horizontally. The San Andreas Fault in California is the most famous example, marking the boundary between the Pacific Plate and the North American Plate. Here, the Pacific Plate moves northwestward relative to North America at about 5 centimeters per year. This motion is not smooth. The plates lock against each other, building up stress over decades or centuries, then release it suddenly in earthquakes. The 1906 San Francisco earthquake resulted from a rupture along approximately 480 kilometers of the fault, with horizontal displacement of up to 6 meters in some locations. The energy that drives all this motion is substantial, but diffuse. The total heat flow from the Earth's interior to the surface is approximately 47 terawatts, roughly 3 times the total energy consumption of human civilization. Most of this heat escapes through the oceanic crust, which is thinner and younger than continental crust. The oldest oceanic crust on Earth is only about 200 million years old, found in the Western Pacific. Anything older has been recycled back into the mantle through subduction. Continental crust, by contrast, can persist for billions of years. The oldest known continental rocks, found in the Canadian Shield and in Western Australia, date to approximately 4 billion years ago, nearly as old as the Earth itself. This recycling of oceanic crust through subduction and creation at mid-ocean ridges means that the ocean floors are constantly being renewed. The Atlantic Ocean did not exist 200 million years ago. The Pacific Ocean is slowly shrinking as plates around its margins subduct beneath the surrounding continents. In perhaps 250 million years, the Pacific may close entirely, bringing the Americas into collision with Asia and Australia, forming a new supercontinent. This is the rhythm of plate tectonics, a slow pulse of assembly and dispersal that has repeated multiple times throughout Earth's history, each cycle lasting hundreds of millions of years, each cycle rearranging the geography of the world and reshaping the conditions for life. The supercontinents that have formed and broken apart across Earth's history are not random accidents. They are inevitable consequences of the convection currents deep within the mantle, the same currents that drive the plates across the surface at rates measured in centimeters per year. When plates collide, they have nowhere else to go. Continents, being too buoyant to subduct, pile into one another, crumpling their edges into mountain ranges and welding themselves together over tens of millions of years. And when the mantle beneath these assembled landmasses grows too hot, trapped by the insulating blanket of continental crust above, new rifts tear the supercontinent apart, beginning the cycle anew. The oldest supercontinent we have reasonable evidence for is called Valbara, a small landmass that may have existed around 3.6 billion years ago, formed from the collision of the Kaap-Val Craton of southern Africa and the Pilbara Craton of Western Australia. The evidence is subtle, written in matching sequences of ancient rocks, in the alignment of magnetic minerals that recorded the orientation of Earth's magnetic field at the time of their formation. These paleomagnetic signatures suggest that these two pieces of ancient crust, now separated by the Indian Ocean, once sat side by side. After Valbara came Ur, around 3 billion years ago. Then Knorrland, approximately 2.7 billion years ago. These early supercontinents were smaller than their later successors, assembled from the limited continental crust that had formed by that point in Earth's history. The continents were still growing, still being built by the slow accumulation of volcanic material at subduction zones and the gradual differentiation of lighter silicate minerals from the mantle. By 1.8 billion years ago, a larger supercontinent had assembled. Columbia, also called Nuna, stretched across the equator, a vast landmass that included the cores of what would become North America, Greenland, Scandinavia, Siberia, and parts of South America, Africa, India, and Australia. The evidence for Columbia comes from matching geological formations across these now distant continents, from the alignment of ancient mountain belts that once formed continuous chains, and from the paleomagnetic data locked in rocks of that age. Columbia held together for perhaps 300 million years before rifting apart around 1.5 billion years ago. The breakup of Columbia scattered its fragments across the globe, but the relentless motion of the plates eventually brought them back together. Around 1.1 billion years ago, a new supercontinent began to assemble. This was Rodinia, a name derived from the Russian word for homeland, and it would become one of the most significant land masses in Earth's history. Rodinia's assembly was marked by a series of mountain-building events called the Grenville orogeny, which created a belt of mountains stretching from what is now Texas through eastern North America, across Scandinavia, and into Australia. These mountains, now eroded to their roots, were once as tall as the modern Himalayas, built by the collision of continental blocks over a period of nearly 200 million years. The Grenville Mountains reached their peak around 1.0 billion years ago, a range of peaks perhaps 8,000 meters high, their slopes covered in bare rock because land plants had not yet evolved. Rodinia sat centered roughly over the equator, a configuration that would have profound consequences for Earth's climate. The supercontinent blocked the circulation of ocean currents, preventing the distribution of heat from the tropics to the poles. At the same time, the weathering of the vast continental surface consumed carbon dioxide from the atmosphere, reducing the greenhouse effect. The combination of these factors may have triggered the most severe ice ages in Earth's history. Between 720 and 635 million years ago, during the period called the Cryogenian, Earth experienced at least 2 episodes of extreme glaciation. Ice sheets advanced from the poles toward the equator, covering nearly the entire planet in what scientists call snowball Earth events. Glacial deposits from this period have been found in rocks that paleomagnetic evidence places at tropical latitudes, suggesting that ice reached almost to the equator. The Sturtian glaciation lasted from approximately 717 to 660 million years ago, followed by the Marinoan glaciation from about 650 to 635 million years ago. During these events, global average temperatures may have dropped to -50 degrees Celsius, and ice thickness at the equator may have reached 1 kilometer. Rodinia was already breaking apart when these glaciations occurred. The supercontinent began to rift around 750 million years ago, as mantle plumes rose beneath the continental interior, heating and stretching the crust until it fractured. The rifting created new ocean basins, including the precursor to the Pacific Ocean, called the Panthalassic Ocean. By 600 million years ago, Rodinia had fragmented into several smaller continents, scattered across the globe. The breakup of Rodinia set the stage for the next great assembly. The continental fragments drifted, collided, and merged over the following 350 million years, gradually coalescing into a new supercontinent. This process was not smooth or uniform. Different pieces came together at different times, creating intermediate configurations that some researchers have given names like Pannotia or Gondwana. Gondwana itself was a massive southern landmass that assembled around 550 million years ago from the collision of what would become South America, Africa, Antarctica, Australia, India, and Arabia. This assembly was marked by the Pan-African orogeny, a series of mountain-building events that welded these continental blocks together along sutures that can still be traced today. Gondwana would persist as a coherent landmass for over 300 million years, even as it drifted and eventually merged with the northern continents. The final assembly of Pangaea, the most recent supercontinent, occurred around 335 million years ago, during the Carboniferous period. The collision of Gondwana with the northern landmass of Laurussia created the Appalachian Mountains in eastern North America, the Variscan Mountains in Europe, and the Ural Mountains that now divide Europe from Asia. These mountain ranges, though now much reduced by erosion, were once towering peaks comparable to the modern Alps or Rockies. Pangaea stretched from pole to pole, a C-shaped landmass wrapped around a partially enclosed ocean called the Tethys Sea. The interior of the supercontinent was vast and dry, far from the moderating influence of the oceans. Deserts spread across what would become the American Southwest, Europe, and North Africa. The climate was characterized by extreme seasonality, with monsoons driven by the differential heating of land and sea. The assembly of Pangaea had profound effects on life. The joining of previously separate land masses allowed species to migrate across the entire supercontinent, homogenizing faunas that had evolved in isolation. The fossil record shows that many groups of reptiles and early mammals spread rapidly across Pangaea during the Permian and Triassic periods. At the same time, the reduction in coastline and the loss of shallow marine habitats may have contributed to the severity of the end Permian mass extinction 252 million years ago, the most devastating extinction event in Earth's history. Pangaea began to break apart around 200 million years ago, as a new rift opened between what would become North America and Africa. This rift would eventually become the Atlantic Ocean, which today widens by approximately 2.5 centimeters per year. The separation was not instantaneous. South America remained connected to Africa until about 130 million years ago. India broke away from Antarctica and began its long northward journey around 120 million years ago, eventually colliding with Asia to form the Himalayas starting around 50 million years ago. Australia separated from Antarctica approximately 45 million years ago and continues to drift northward at about 7 centimeters per year. The fragments of Pangaea are still moving today, still driven by the same convection currents that have operated for billions of years. The Atlantic continues to widen, the Pacific continues to shrink. Africa is slowly rotating counterclockwise and pushing into Europe, gradually closing the Mediterranean Sea. In perhaps 50 million years, the Mediterranean will be gone, replaced by a mountain range as tall as the Himalayas. In 250 million years, the continents may reassemble into a new supercontinent, which some researchers have named Pangaea Proxima or Amasia, depending on the model used to predict future plate motions. The collision of continents does not simply crumple the crust like paper. It builds mountains through a process called orogeny, a term derived from the Greek words for mountain and birth. Every major mountain range on Earth today exists because two tectonic plates converged, and the immense forces generated by that convergence had nowhere to go but up. Consider the Himalayas, the tallest mountain range on the planet. They began forming approximately 50 million years ago, when the Indian subcontinent, which had been traveling northward at a relatively rapid 15 centimeters per year, collided with the Eurasian plate. Before this collision, India was an island continent, separated from Asia by the Tethys Sea, an ancient ocean that no longer exists. As India pushed into Asia, the oceanic crust of the Tethys was subducted beneath the Eurasian plate, diving down into the mantle where it was recycled. But continental crust is less dense than oceanic crust. It cannot sink. When the continental crust of India met the continental crust of Asia, neither plate could subduct. Instead, the crust buckled, folded, and thrust upward. The rate of this uplift is measurable. The Himalayas rise by approximately 5 millimeters per year, though this figure varies across different parts of the range. Mount Everest, currently standing at 8,849 meters above sea level, grows taller each year, though erosion simultaneously works to wear it down. The balance between uplift and erosion determines the actual height of any mountain at any given moment. If uplift exceeds erosion, the mountain grows. If erosion exceeds uplift, the mountain shrinks. The Himalayas are still in their youth, geologically speaking, because the collision that created them continues today. India still pushes into Asia at roughly 4 to 5 centimeters per year, and the crust continues to deform under that pressure. The mechanics of this deformation involve several distinct processes. Folding occurs when layers of rock bend under compressive stress, creating wave-like structures that can span kilometers. Faulting occurs when the stress exceeds the strength of the rock, causing it to fracture and shift along planes called thrust faults. In the Himalayas, enormous sheets of rock have been pushed up and over one another along these faults, stacking like shingles on a roof. The main central thrust, one of the major fault systems in the Himalayas, has displaced rock by more than 100 kilometers horizontally, while also lifting it vertically. The Alps formed through a similar process, though on a smaller scale. Beginning around 65 million years ago, the African plate began pushing northward into the Eurasian plate, closing the western portion of the Tethys Sea. The collision crumpled the crust between them, creating the Alps, the Pyrenees, and the mountains of the Mediterranean region. The Alps continue to rise at approximately 1 to 2 millimeters per year, though they are older and more eroded than the Himalayas. Their peaks, while impressive, rarely exceed 4,800 meters. The Appalachian Mountains of eastern North America tell a different story. They are ancient, formed during multiple orogenic events spanning hundreds of millions of years. The earliest phase, the Taconic orogeny, occurred approximately 450 million years ago when volcanic island arcs collided with the eastern margin of the ancestral North American continent, called Laurentia. The Akkadian orogeny followed around 375 million years ago, adding more material to the growing mountain belt. The final and most dramatic phase, the Alleghenian orogeny, occurred between 325 and 260 million years ago, when the African portion of Gondwana collided with Laurentia during the assembly of Pangaea. At their peak, the Appalachians may have rivaled the modern Himalayas in height, with summits possibly exceeding 6,000 meters. Today, their highest point, Mount Mitchell, reaches only 2,037 meters. The difference represents 300 million years of erosion, the patient work of water, ice, and wind dismantling what tectonics had built. The rounded, gentle profiles of the Appalachians contrast sharply with the jagged peaks of the Himalayas, and this contrast reflects their relative ages. Young mountains are sharp because erosion has not yet had time to smooth them. Old mountains are soft because erosion has been working on them for hundreds of millions of years. The Andes of South America represent a third type of orogeny, one driven not by continent-continent collision, but by the subduction of oceanic crust beneath continental crust. The Nazca Plate, a slab of oceanic lithosphere in the eastern Pacific, dives beneath the South American plate at a rate of approximately 7 centimeters per year. As it descends, it generates friction and heat, melting portions of the mantle above it. This molten rock rises to form volcanoes along the length of the Andes. Simultaneously, the compressive forces generated by subduction cause the overlying continental crust to fold and thrust upward. The Andes have been building for approximately 200 million years, though the most dramatic uplift occurred within the last 50 million years. Aconcagua, the highest peak in the Andes at 6,961 meters, stands as evidence of this ongoing process. The forces involved in orogeny are immense but slow. The pressure exerted by colliding plates can reach hundreds of megapascals, enough to deform solid rock over geological timescales. Rock that would shatter under a sudden impact will flow like putty when subjected to sustained pressure over millions of years. This behavior, called ductile deformation, allows deep crustal rocks to fold into complex shapes without fracturing. Closer to the surface, where temperatures and pressures are lower, rocks behave more brittly, fracturing along faults rather than folding. The heat generated during orogeny also transforms rocks through a process called metamorphism. Shale, a sedimentary rock formed from compressed mud, becomes slate under low-grade metamorphism. With more heat and pressure, slate becomes phyllite, then schist, then gneiss. Limestone transforms into marble. Sandstone becomes quartzite. The metamorphic rocks exposed in mountain cores record the temperatures and pressures they experienced during burial and deformation. Geologists can read these rocks like a history book, reconstructing the conditions that existed tens of kilometers below the surface millions of years ago. The Caledonian orogeny, which occurred between 490 and 390 million years ago, built mountains across what is now Scotland, Scandinavia, and the eastern coast of Greenland. These mountains formed where the continents of Laurentia, Baltica, and Avalonia collided, closing the Iapetus Ocean. The Scottish Highlands are the eroded remnants of this ancient range. The rocks exposed there include gneisses that formed at depths of 20 kilometers or more, brought to the surface by hundreds of millions of years of uplift and erosion. Mountains do not simply rise and then stop. They exist in a dynamic equilibrium between the forces that build them and the forces that destroy them. Isostasy, the principle that the crust floats on the denser mantle beneath it, plays a crucial role in this balance. As erosion removes material from the top of a mountain range, the crust becomes lighter and rises in response, like a boat rising in the water as cargo is unloaded. This isostatic rebound can extend the life of a mountain range, bringing deeper rocks to the surface even as the peaks are worn away. The very forces that lift mountains into the sky begin their work of destruction from the moment the first rocks breach the surface. Erosion and weathering are not separate from mountain building, but are its constant companions, working in opposition to the tectonic forces that push the crust upward. The Himalayas, rising at a rate of approximately 5 millimeters per year, lose nearly the same amount to erosion annually. This is the dynamic equilibrium that governs all mountain ranges, a slow-motion battle between the heat engine of the Earth's interior and the relentless action of water, ice, wind, and chemistry at the surface. Weathering begins at the molecular level, in the spaces between atoms within crystalline structures. When rainwater falls through the atmosphere, it absorbs carbon dioxide and becomes a weak carbonic acid, with a pH of approximately 5.6. This slightly acidic water seeps into the microscopic fractures and grain boundaries of exposed rock, initiating chemical reactions that slowly dismantle the mineral lattices that took millions of years to form. Feldspar, one of the most abundant minerals in the Earth's crust, reacts with carbonic acid to produce clay minerals, silica, and dissolved ions of potassium, sodium, and calcium. A single feldspar crystal that crystallized from magma 200 million years ago can be reduced to clay particles in a few thousand years of exposure to rainwater. The process of hydrolysis, where water molecules directly participate in breaking chemical bonds, is particularly effective against silicate minerals. The silicon-oxygen bonds that form the backbone of most rock-forming minerals are slowly severed as hydrogen ions from water replace metal cations in the crystal structure. This chemical dismantling proceeds atom by atom, molecule by molecule, transforming solid granite into loose grains of quartz surrounded by soft clay. The quartz grains, composed of pure silicon dioxide, resist this chemical attack far more effectively than feldspar or mica, which is why sandy beaches around the world are dominated by quartz crystals that have survived the journey from mountain peak to coastline. Temperature plays a crucial role in accelerating these chemical reactions. For every 10 degrees Celsius increase in temperature, the rate of most chemical weathering reactions approximately doubles. This explains why tropical regions experience far more rapid chemical weathering than polar environments. In the Amazon basin, where temperatures remain consistently above 25 degrees Celsius and rainfall exceeds 2,000 millimeters per year, the weathering front can penetrate more than 100 meters into the bedrock. The resulting deep soils, called laterites, are so thoroughly leached of their original minerals that they consist primarily of iron and aluminum oxides, giving them their characteristic red color. Physical weathering works alongside these chemical processes, breaking rock into smaller pieces and exposing fresh surfaces to chemical attack. Frost wedging is among the most powerful of these mechanical forces. When water seeps into cracks in rock and freezes, it expands by approximately 9%. This expansion generates pressures that can exceed 200 megapascals, far greater than the tensile strength of most rocks, which typically ranges from 5 to 20 megapascals. In alpine environments where temperatures oscillate above and below freezing hundreds of times per year, this repeated freezing and thawing can shatter solid rock into angular fragments called scree or talus, which accumulate in great aprons at the base of cliffs. The roots of plants contribute to this mechanical breakdown in ways that seem gentle but are remarkably persistent. A tree root growing into a crack in bedrock exerts a pressure of only about 1.5 megapascals, far less than freezing water. But roots grow continuously for decades or centuries, slowly widening fractures millimeter by millimeter. The roots of a mature oak tree can extend more than 20 meters from the trunk, probing every weakness in the underlying rock. When the tree eventually dies and the roots decay, they leave behind channels that allow water to penetrate deeper into the rock, accelerating both chemical and physical weathering. Once rock has been broken down by weathering, erosion transports the resulting sediment away from its source. Gravity is the fundamental driver of all erosion, pulling water, ice, and loose material downslope towards the sea. Rivers are the primary agents of sediment transport on Earth, carrying an estimated 20 billion tons of material to the oceans each year. The Amazon River alone delivers approximately 1.2 billion tons of sediment annually, enough to bury the entire city of London under several meters of mud each year if it could be concentrated in one place. The erosive power of a river depends on its velocity and the volume of water it carries. The kinetic energy of flowing water increases with the square of its velocity, meaning that a river flowing at 4 meters per second has 16 times the erosive power of one flowing at 1 meter per second. During floods, when velocities and volumes both increase dramatically, rivers can move boulders weighing several tons, carving deep channels into bedrock and reshaping landscapes in hours or days. The Colorado River, over the past 6 million years, has carved the Grand Canyon to a depth of more than 1,800 meters, removing approximately 4,000 cubic kilometers of rock and sediment. Glaciers are even more effective erosive agents than rivers, though they work far more slowly. A glacier is essentially a river of ice, flowing downhill under its own weight at rates typically measured in meters per year rather than meters per second. The Jakobshavn Glacier in Greenland, one of the fastest-moving glaciers on Earth, advances at approximately 40 meters per day, but most glaciers move at speeds of 10 to 200 meters per year. Despite this slow pace, glaciers carry enormous erosive power because of the rocks frozen into their bases. These embedded stones act like sandpaper, grinding against the bedrock beneath the ice and producing fine-grained sediment called glacial flour. The milky blue-green color of glacial lakes comes from this rock flour suspended in the water, scattering light in the same way that milk appears white. The distinctive U-shaped valleys found in mountainous regions around the world are the signature of glacial erosion. Rivers carve V-shaped valleys because they erode primarily at the bottom of their channels, but glaciers erode both the floor and the walls of the valleys they occupy, widening them into broad troughs with steep sides. Yosemite Valley in California, carved by glaciers during the Pleistocene ice ages, has walls that rise more than 900 meters above the valley floor, polished smooth by the passage of ice that was itself more than 600 meters thick. Wind erosion operates most effectively in arid environments where vegetation is sparse and loose sediment is exposed to the atmosphere. The process of deflation removes fine particles from the surface, leaving behind a lag deposit of larger stones called desert pavement. In the Sahara Desert, wind erosion has excavated vast depressions called deflation hollows, some of which extend below sea level. The Qattara Depression in Egypt, at 134 meters below sea level, was carved primarily by wind over millions of years. The sand removed from these depressions accumulates in dune fields that can cover thousands of square kilometers and contain individual dunes more than 300 meters tall. The sediment produced by weathering and transported by erosion does not simply disappear. It accumulates in basins, river deltas, and ocean floors, beginning the next phase of the rock cycle. The Mississippi River Delta, built from sediment eroded from the Rocky Mountains, the Appalachians, and everything in between, extends more than 150 kilometers into the Gulf of Mexico. This sediment, compressed and lithified over millions of years, will eventually become sedimentary rock, which may one day be uplifted by tectonic forces to form new mountains, beginning the cycle again. The sediment that settles in those basins and deltas does not remain loose sand and mud forever. It undergoes a transformation so gradual that it would be imperceptible to any observer, yet so profound that it converts soft, unconsolidated particles into solid rock. This process, called lithification, operates through two primary mechanisms: compaction and cementation, both driven by the relentless accumulation of material above and the slow percolation of mineral-rich water through the spaces between grains. Consider a single grain of quartz, weathered from a granite outcrop in what is now the Canadian Shield, carried by meltwater into a river, tumbled downstream for hundreds of kilometers, and finally deposited in a shallow sea. That grain settles onto the sea floor alongside billions of others, each with its own journey. At first, the sediment is loose, saturated with water, with perhaps 60% of its volume, consisting of empty pore space between the grains. But more sediment arrives, layer upon layer, year after year, millennium after millennium. The weight of the overlying material presses down with increasing force. At a depth of just 100 meters, the pressure has already squeezed out much of the water and reduced the porosity to perhaps 40%. At 500 meters, the grains are pressed so tightly together that they begin to interlock, their porosity dropping to 25% or less. This compaction alone can reduce the thickness of a sediment layer by half. Mudstones, composed of clay particles smaller than 4 micrometers in diameter, compact more dramatically than sandstones because the flat, platy clay minerals can rotate and stack more efficiently under pressure. A layer of mud that was originally 10 meters thick might compact to just 2 meters of shale over millions of years. But compaction alone does not create solid rock. The spaces between grains must be filled with mineral cement, precipitated from groundwater that flows slowly through the sediment. This cementation process depends entirely on the chemistry of the water and the temperature and pressure conditions at depth. Silica cement, composed of silicon dioxide, precipitates when silica-saturated water cools or when the concentration of dissolved silica exceeds the saturation point. Calcite cement, calcium carbonate, forms in waters rich in dissolved calcium and carbonate ions, particularly in marine environments where the shells of countless organisms contribute these ions to the pore water. Iron oxide cements give sandstones their characteristic red and orange colors, while clay minerals can fill pore spaces in finer grained sediments. The rate of cementation varies enormously depending on local conditions. In some environments, sediments can become partially lithified within thousands of years. In others, the process takes tens of millions of years. The Navajo sandstone of the American Southwest, those sweeping cross-bedded cliffs of petrified sand dunes, accumulated during the Jurassic period between 190 and 174 million years ago. The silica cement that binds its grains was deposited over millions of years as groundwater circulated through the buried dune field, dissolving silica from some grains and precipitating it in the pore spaces between others. The sedimentary rocks formed through these processes preserve within their structure a detailed record of the conditions under which they formed. Grain size reveals the energy of the depositional environment. Coarse gravels indicate fast-moving water or steep slopes, while fine clays settle only in still water. Sorting the uniformity of grain sizes indicates the duration and consistency of transport. Well-sorted sand, with grains of nearly identical size, has been winnowed by wind or waves that removed both the finer and coarser particles. Poorly sorted sediment, with grains ranging from clay to pebbles, was deposited rapidly, perhaps by a flood or debris flow that lacked the time or energy to separate particles by size. The shapes of sedimentary structures tell their own stories. Ripple marks preserved in sandstone record the direction and strength of ancient currents. Mud cracks indicate that the sediment dried out, exposed to air, before being buried by the next layer. Graded bedding, where grain size decreases from bottom to top within a single layer, records the settling of particles from a turbulent suspension, the coarsest and heaviest grains falling first, the finest last. These structures, frozen in stone, allow geologists to reconstruct environments that vanished hundreds of millions of years ago. But the rock cycle does not end with lithification. Sedimentary rocks, once formed, can be transformed again through heat and pressure into metamorphic rocks, their original textures and minerals altered beyond recognition. When a sedimentary basin is caught between colliding continents, the rocks within it are subjected to temperatures and pressures far beyond those of simple burial. At temperatures above 200 degrees Celsius and pressures equivalent to burial depths of several kilometers, the minerals within sedimentary rocks begin to recrystallize. Shale, that fine-grained rock formed from compacted mud, transforms first into slate as the clay minerals realign perpendicular to the direction of maximum pressure, creating the characteristic slaty cleavage that allows the rock to split into thin, flat sheets. With increasing temperature and pressure, slate becomes phyllite, its surface taking on a silky sheen as the mica crystals grow larger. Further metamorphism produces schist, in which the mica crystals are visible to the naked eye, creating a rock that sparkles and splits along wavy foliation plains. At the highest grades of metamorphism, schist transforms into gneiss, a banded rock in which light and dark minerals have segregated into distinct layers, the original sedimentary texture completely obliterated. Limestone undergoes its own metamorphic journey. The calcium carbonate crystals that compose it recrystallize into larger interlocking grains of calcite, producing marble. The fossils that may have been preserved in the original limestone are destroyed, their delicate structures consumed by the growing crystals. Pure limestone produces white marble, but impurities create the colored varieties prized by sculptors. Iron oxides produce pink and red, carbon produces gray and black, serpentine produces green. Sandstone, when metamorphosed, becomes quartzite, one of the hardest and most resistant rocks on Earth. The original quartz grains fuse together, their boundaries disappearing as the silica recrystallizes into an interlocking mosaic. Unlike sandstone, which breaks around its grains, quartzite fractures through them, producing smooth, curved surfaces that glint in the light. The temperatures required for these transformations are not arbitrary. They correspond to specific mineral stability fields, the ranges of temperature and pressure within which particular minerals can exist. Chlorite, a green mineral common in low-grade metamorphic rocks, is stable up to about 450 degrees Celsius. Above that temperature, it breaks down, and its components recombine to form biotite and garnet. Garnet itself is stable up to about 700 degrees Celsius in typical crustal compositions. These mineral assemblages serve as geological thermometers and barometers, allowing geologists to determine the conditions deep within ancient mountain belts. But even metamorphic rocks are not the end of the cycle. If temperatures exceed approximately 700 to 900 degrees Celsius, depending on the rock composition and the presence of water, the rock begins to melt. This partial melting, called anatexis, produces magma that can rise through the crust, cool and crystallize into igneous rock. The cycle has returned to its beginning. The time required for a complete circuit of the rock cycle defies easy comprehension. A grain of quartz weathered from a granite pluton might spend 10 million years being transported to the sea, 50 million years buried in a sedimentary basin, another 100 million years being metamorphosed in a mountain belt, and then be melted and incorporated into a new magma that crystallizes into granite. The entire journey might span 300 million years or more, yet it is merely one of countless cycles that have operated continuously since the Earth's crust first solidified more than 4 billion years ago. The rock cycle is powered by two great engines. The first is the internal heat of the Earth, the residual warmth from planetary accretion combined with the steady decay of radioactive elements in the mantle and crust. This heat drives mantle convection, which moves tectonic plates, builds mountains, and creates the conditions for metamorphism and melting. The second engine is the sun, whose energy drives the water cycle, the winds, and the temperature variations that weather rock and transport sediment. These two engines, one internal and one external, have operated in tandem for billions of years, continuously recycling the materials of the crust. Within those ancient minerals, locked inside the crystalline lattices of zircon and feldspar and mica, another kind of clock has been ticking since the moment each crystal formed. This clock does not depend on the movement of plates, or the flow of water, or the energy of the sun. It operates at the level of individual atoms, governed by the fundamental forces that hold atomic nuclei together, and it runs with a precision that no geological process can match. Radioactive decay is the spontaneous transformation of unstable atomic nuclei into more stable configurations. Certain isotopes, variants of elements that contain different numbers of neutrons in their nuclei, exist in states of inherent instability. The forces that bind protons and neutrons together in the nucleus are immensely powerful, but in some configurations, these forces are not quite sufficient to maintain permanent cohesion. Over time, these unstable nuclei will emit particles or energy, transforming into different elements entirely. This process cannot be hurried or slowed by any external condition. Temperature does not affect it. Pressure does not affect it. Chemical reactions leave it unchanged. The decay proceeds at a rate determined solely by the quantum mechanical properties of the nucleus itself. The concept of half-life describes this decay in statistical terms. Uranium-238, one of the most important isotopes for geological dating, has a half-life of approximately 4.468 billion years. This means that if you begin with a collection of uranium-238 atoms after 4.468 billion years, exactly half of them will have decayed into thorium-234, which itself decays through a series of intermediate steps until it eventually becomes lead-206, a stable isotope that will persist indefinitely. After another 4.468 billion years, half of the remaining uranium will have decayed, leaving 1/4 of the original amount. This exponential decay continues predictably, each half-life reducing the parent isotope by exactly 50%. The Earth itself is approximately 4.54 billion years old, a figure determined primarily through the analysis of uranium-lead ratios in the oldest known minerals. Zircon crystals from the Jack Hills region of Western Australia have been dated to 4.4 billion years, making them the oldest known terrestrial materials. These tiny crystals, some no larger than a grain of sand, incorporated uranium atoms into their crystal structure when they first formed from cooling magma. At that moment, the clock began. The uranium atoms have been decaying steadily ever since, and by measuring the precise ratio of uranium, 238 to lead 206 within these crystals, scientists can calculate exactly how much time has passed since crystallization. The mathematics of this calculation are elegant in their simplicity. If a mineral contains equal amounts of uranium-238 and lead-206, and if all the lead present was produced by uranium decay rather than being incorporated during crystal formation, then exactly one half-life has elapsed since the mineral formed. If the ratio is 3 parts lead to 1 part uranium, then 2 half-lives have passed, because the original uranium has been halved twice. By measuring these ratios with mass spectrometers capable of detecting individual atoms, geologists can determine ages with uncertainties of less than 1%, even for rocks billions of years old. Potassium-40 provides another crucial chronometer, particularly useful for dating younger rocks and volcanic deposits. This isotope decays into argon-40 with a half-life of 1.25 billion years. When volcanic rock solidifies from lava, any argon gas present escapes into the atmosphere, resetting the clock to 0. As the rock ages, potassium-40 atoms within its minerals slowly transform into argon-40, which remains trapped in the crystal lattice. By measuring the ratio of potassium to argon, scientists can determine when the volcanic eruption occurred. This technique has been used to date the basalt flows that covered the Luna Maria, the volcanic rocks that preserve early human fossils in East Africa, and the ash layers that mark mass extinction events in the geological record. Carbon-14 operates on a much shorter timescale, with a half-life of only 5,730 years. This isotope is continuously produced in the upper atmosphere when cosmic rays strike nitrogen atoms, and it is incorporated into living organisms through photosynthesis and the food chain. While an organism is alive, it maintains a constant ratio of carbon-14 to stable carbon-12 because it continuously exchanges carbon with its environment. At death, this exchange ceases, and the carbon-14 begins to decay without replacement. By measuring the remaining carbon-14 in organic materials such as wood, bone, or shell, archaeologists can determine when the organism died. This technique is effective for materials up to approximately 50,000 years old, beyond which the remaining carbon-14 becomes too scarce to measure accurately. The decay chains of heavy elements reveal the deep history of matter itself. Uranium-238 does not transform directly into lead-206. Instead, it passes through 14 intermediate steps, emitting alpha particles and beta particles, creating a sequence of daughter isotopes that includes thorium, radium, radon, polonium, and bismuth. Each step in this chain has its own characteristic half-life, ranging from billions of years to fractions of a second. Radon-222, a radioactive gas that can accumulate in basements and pose health risks, is a product of this decay chain, continuously generated by the uranium present in soil and rock. The entire chain represents a slow cascade of nuclear transformations that has been proceeding since the uranium atoms were first synthesized in the cores of massive stars and in the violent collisions of neutron stars, billions of years before our solar system formed. The heat generated by radioactive decay is not negligible. Approximately half of the Earth's internal heat budget comes from the decay of uranium-238, uranium-235, thorium-232, and potassium-40 distributed throughout the mantle and crust. This radiogenic heat, amounting to roughly 20 terawatts of continuous power, helps drive the mantle convection that moves tectonic plates. Without radioactive decay, the Earth would have cooled more rapidly. Plate tectonics might have ceased billions of years ago, and the geological processes that recycle carbon and regulate climate would have ground to a halt. The same atomic instability that provides our most precise clocks also provides the energy that keeps our planet geologically active. Rubidium-87 decays to strontium-87 with a half-life of 48.8 billion years, more than 10 times the current age of the universe. This extraordinarily slow decay makes rubidium-strontium dating useful for the oldest rocks and for understanding the differentiation of planetary bodies. Samarium-147 decays to neodymium-143 with a half-life of 106 billion years, providing insights into the earliest history of the solar system. These long-lived isotopes preserve information about events that occurred before the Earth existed, when the solar nebula was still condensing from interstellar gas and dust. The precision of radiometric dating has transformed our understanding of Earth history. Before these techniques were developed in the 20th century, geologists could determine only relative ages, knowing that one rock layer was older than another, but unable to assign absolute dates. The discovery that radioactive decay provided a natural clock allowed the construction of a quantitative timescale. The Cambrian explosion of animal life, once vaguely placed in the distant past, is now dated to approximately 538.8 million years ago. The extinction of the non-avian dinosaurs occurred 66 million years ago, a date confirmed by multiple independent isotopic systems applied to the clay layer that marks the impact event. The emergence of our own species, Homo sapiens, is dated to roughly 300,000 years ago, based on thermoluminescence and argon-argon dating of associated volcanic deposits. These atomic clocks tick on, indifferent to the processes occurring around them, measuring time with quantum mechanical precision while continents drift and mountains rise and species evolve and go extinct. The same uranium atoms that crystallized in the first zircons of the young Earth continue their patient transformation into lead, marking the passage of billions of years, one decay event at a time. While those uranium atoms continued their patient decay within ancient zircons, something far more improbable was beginning to stir in the shallow pools and hydrothermal vents of the young Earth. The same radioactive elements that now serve as geological clocks were, 4 billion years ago, providing heat and energy to a planet whose surface was finally cool enough to hold liquid water, yet still warm enough to drive the chemical reactions that would eventually blur the line between chemistry and biology. The Earth of 4.4 billion years ago was a world of extremes. The atmosphere contained no free oxygen, instead consisting primarily of nitrogen, carbon dioxide, water vapor, and trace amounts of methane and ammonia. The surface temperature hovered around 70 to 80 degrees Celsius in many regions. kept warm by the greenhouse effect of that dense carbon dioxide atmosphere, and by the residual heat still radiating from the planet's formation. Volcanic activity was perhaps 10 times more intense than today, releasing gases and minerals into the oceans at rates that would seem catastrophic by modern standards. Yet these conditions, hostile as they appear, were precisely what was needed for the chemistry of life to begin. The raw materials were simple and abundant. Hydrogen, the most common element in the universe, was present in water and in gases escaping from volcanic vents. Carbon, forged in the cores of ancient stars, existed in carbon dioxide dissolved in the oceans and in organic molecules delivered by meteorites and comets. Nitrogen filled the atmosphere. Phosphorus and sulfur emerged from volcanic emissions and mineral weathering. These 6 elements, hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, would become the alphabet of life, combining in countless arrangements to spell out the molecular words of biology. The transition from simple molecules to the complex chemistry of life required energy, and the young Earth provided it in abundance. Ultraviolet radiation from the sun, unfiltered by any ozone layer, bombarded the surface with intensities perhaps 100 times greater than today. Lightning storms, far more frequent in that turbulent atmosphere, discharged enormous electrical energy into the air and water. Hydrothermal vents on the ocean floor, where seawater met magma at temperatures exceeding 400 degrees Celsius, created steep chemical gradients that could drive reactions impossible under ordinary conditions. Radioactive decay within the crust and mantle contributed additional energy, heating groundwater and creating warm, chemically active environments in porous rocks. The Miller-Urey experiment of 1953 demonstrated that amino acids, the building blocks of proteins, could form spontaneously when electrical discharges passed through a mixture of water, methane, ammonia, and hydrogen. Within just 1 week, the experiment produced glycine, alanine, and several other amino acids, proving that the fundamental components of life could arise from simple chemistry without any biological intervention. Subsequent experiments, using more realistic atmospheric compositions and various energy sources, have produced an even wider range of organic molecules, including sugars, lipids, and the nucleotide bases that form the backbone of DNA and RNA. Yet amino acids and nucleotides are merely the letters of the biological alphabet. The real challenge lies in assembling them into functional words and sentences, into proteins that can catalyze reactions and nucleic acids that can store and transmit information. This assembly requires not just the right molecules but the right conditions, surfaces that can concentrate and organize reactants, energy sources that can drive polymerization, and environments that can protect fragile molecular chains from immediate destruction. Clay minerals may have played a crucial role in this organization. The layered structure of clays like montmorillonite provides vast surface areas where organic molecules can absorb and concentrate. Experiments have shown that RNA nucleotides can polymerize into chains up to 50 units long when incubated with montmorillonite clay, a process that occurs spontaneously at temperatures between 25 and 75 degrees Celsius. The negatively charged surfaces of clay particles attract positively charged organic molecules, bringing them into close proximity and orienting them in ways that favor chemical bonding. In a sense, these mineral surfaces acted as primitive catalysts, accelerating reactions that would otherwise occur too slowly to matter. Hydrothermal vents offer another compelling environment for life's origin. The alkaline vents discovered at the Lost City hydrothermal field in the Atlantic Ocean produce warm, mineral-rich fluids at temperatures of 40 to 90 degrees Celsius, far cooler than the superheated black smokers, but chemically more hospitable to organic synthesis. The porous mineral structures of these vents, composed of calcium carbonate and other precipitates, create countless tiny compartments that could have served as primitive cell-like enclosures. The chemical gradient between the alkaline vent fluid and the slightly acidic early ocean would have provided a natural proton gradient, similar to the gradients that modern cells use to generate energy through chemiosmosis. The emergence of self-replicating molecules represents the critical threshold between chemistry and biology. The RNA world hypothesis proposes that RNA, rather than DNA, was the first molecule capable of both storing genetic information and catalyzing chemical reactions. Unlike DNA, which requires protein enzymes to replicate, RNA can fold into complex three-dimensional shapes that function as catalysts, called ribozymes. The ribosome itself, the molecular machine that translates genetic information into proteins in all living cells, is fundamentally an RNA catalyst, a molecular fossil from the RNA world preserved across 4 billion years of evolution. Laboratory experiments have created RNA molecules capable of copying other RNA molecules, though with error rates far higher than modern enzymes achieve. These self-replicating ribozymes require carefully controlled conditions and do not yet approach the efficiency of biological systems. Yet they demonstrate that the principle is sound, that molecules can arise which make copies of themselves, and that natural selection can then act upon the variations introduced by copying errors. The encapsulation of these replicating molecules within membrane-bound compartments was another essential step toward cellular life. Fatty acids, simple molecules with a water-attracting head and a water-repelling tail, spontaneously form spherical vesicles when placed in water. These vesicles can grow by incorporating additional fatty acids from their environment and can divide once they become too large to maintain their spherical shape. Experiments have shown that RNA molecules can become trapped inside such vesicles, creating primitive protocells where replication and metabolism can occur in a protected internal environment. The oldest physical evidence of life on Earth comes from rocks in Western Australia and Greenland, dating to approximately 3.5 to 3.8 billion years ago. Stromatolites, layered structures formed by microbial mats, appear in the Pilbara region of Australia in rocks 3.48 billion years old. Carbon isotope ratios in graphite inclusions within 3.7 billion-year-old rocks from Isua, Greenland, show the distinctive signature of biological carbon fixation, with a depletion in carbon-13 relative to carbon-12 that occurs when living organisms preferentially incorporate the lighter isotope. These dates suggest that life emerged remarkably quickly once conditions permitted. The late heavy bombardment, a period of intense asteroid impacts that may have sterilized the Earth's surface, ended approximately 3.8 billion years ago. If life arose within just a few 100 million years after this bombardment ceased, then the transition from prebiotic chemistry to living cells may have been not a miraculous accident, but an almost inevitable consequence of the right chemistry under the right conditions. The first cells were almost certainly simpler than any organism alive today. They likely possessed RNA genomes rather than DNA, used a limited set of amino acids, and relied on environmental chemicals rather than sophisticated metabolic pathways for energy. The transition to DNA-based genomes, which are more stable and can store more information, probably occurred later, as did the evolution of the genetic code that translates nucleotide sequences into protein sequences. This code, nearly universal across all life on Earth, represents a frozen accident from the earliest days of cellular evolution, preserved because any change would be catastrophic to organisms that had already built their entire biochemistry around it. From these humble beginnings, in warm pools or alkaline vents or clay-lined crevices, the first cells began their patient multiplication, dividing perhaps once every few days or weeks, gradually filling the available niches of the young Earth. Each division introduced small errors, variations upon which natural selection could act, beginning the slow accumulation of adaptations that would eventually produce the staggering diversity of life we see today. For hundreds of millions of years after those first cells began their quiet multiplication, the Earth's atmosphere remained a place utterly hostile to the life that would eventually dominate it. The air contained almost no free oxygen, perhaps less than 1 part per million, a concentration so vanishingly small that it would suffocate any modern animal within seconds. Instead, the early atmosphere was rich in nitrogen, carbon dioxide, methane, and water vapor, gases that absorbed and re-radiated heat, keeping the young planet warm despite a sun that shone roughly 30% dimmer than it does today. The early cells that thrived in this environment were anaerobes, organisms whose metabolic machinery had evolved in the absence of oxygen, and for whom that gas would prove not just unnecessary, but actively poisonous. They extracted energy through fermentation and through chemical reactions with sulfur, iron, and other compounds dissolved in the primordial seas. Some developed the ability to harvest energy directly from sunlight, but the earliest forms of photosynthesis did not produce oxygen. These anoxygenic photosynthesizers used hydrogen sulfide or ferrous iron as electron donors, releasing sulfur or ferric iron as waste products, rather than the oxygen that would later transform the world. Then, sometime between 3.4 and 2.7 billion years ago, a group of bacteria developed a new and revolutionary form of photosynthesis. These were the cyanobacteria, sometimes called blue-green algae, though they are not algae at all but true bacteria, and their innovation would prove to be one of the most consequential events in the history of life on Earth. Oxygenic photosynthesis, the process they pioneered, uses water molecules as the source of electrons to power the conversion of carbon dioxide into organic compounds. When a water molecule is split in this reaction, its oxygen atoms are released as a waste product, 2 atoms combining to form a molecule of O2 that drifts away into the surrounding environment. The chemistry of this process is remarkably difficult. Splitting water requires more energy than splitting hydrogen sulfide or other compounds used by earlier photosynthesizers, demanding the evolution of a complex molecular machine called photosystem II. This protein complex contains a cluster of 4 manganese atoms and 1 calcium atom, arranged in a precise geometric configuration that allows them to accumulate the 4 electrons needed to split 2 water molecules. The structure is so intricate and the energetics so demanding that oxygenic photosynthesis appears to have evolved only once in the entire history of life, a singular innovation that all oxygen-producing organisms inherited from those ancient cyanobacterial ancestors. Yet for hundreds of millions of years after cyanobacteria first appeared, the oxygen they produced did not accumulate in the atmosphere. The Earth's surface was rich in reduced compounds, substances hungry for oxygen, that absorbed the gas as quickly as the cyanobacteria could release it. Dissolved iron in the oceans, present at concentrations perhaps 1,000 times higher than in modern seawater, reacted with oxygen to form iron oxides that precipitated out of the water and settled to the sea floor. These deposits, called banded iron formations, preserve a record of this ancient oxygen production in alternating layers of iron-rich and iron-poor sediment, each band representing perhaps a few years or decades of deposition. The total volume of banded iron formations laid down between 3.8 and 1.8 billion years ago represents an almost inconceivable quantity of oxygen, enough to have filled the modern atmosphere many times over, all of it captured and locked away in rust-red stone. Volcanic gases provided another sink for the oxygen being produced. Sulfur dioxide, hydrogen sulfide, and hydrogen gas erupted continuously from the young Earth's more active volcanic systems, and each of these compounds reacted readily with oxygen, removing it from the atmosphere before it could accumulate. The balance between oxygen production and oxygen consumption remained roughly stable for perhaps 1 billion years, with atmospheric oxygen levels hovering near zero, despite the continuous photosynthetic activity of cyanobacterial mats that had spread across the shallow seas and coastal environments of the Archean world. The Great Oxygenation Event, when it finally occurred around 2.4 billion years ago, was not a sudden explosion, but a gradual tipping point, a slow shift in the balance between oxygen sources and oxygen sinks that allowed the gas to begin accumulating in the atmosphere for the first time. The precise trigger remains debated among geochemists, but several factors likely contributed. The burial of organic carbon in sediments removed reduced compounds from the surface environment, leaving more oxygen free to accumulate. The gradual depletion of dissolved iron in the oceans, as it was progressively locked away in banded iron formations, reduced one of the major oxygen sinks. Changes in volcanic activity may have decreased the flux of reduced gases being released into the atmosphere. Whatever the cause, the consequences were profound and nearly catastrophic. Oxygen is a highly reactive molecule, eager to strip electrons from other compounds, and for the anaerobic organisms that had dominated Earth for over 1 billion years, it was a deadly poison. The rise of atmospheric oxygen triggered what some scientists have called the first mass extinction, as anaerobic species were driven from the surface environments they had long inhabited, retreating to oxygen-free refugia in deep sediments, stagnant waters, and the guts of other organisms where their descendants persist to this day. The initial rise brought atmospheric oxygen to perhaps 1 to 2% of modern levels, still far too low to support animal life, but high enough to fundamentally alter the chemistry of the Earth's surface. Iron exposed to the air began to rust, painting the continents in shades of red and orange that had never existed before. Sulfur compounds in the atmosphere oxidized to form sulfate, which dissolved in rainwater and washed into the oceans, changing the chemistry of seawater. The methane that had helped keep the early Earth warm was destroyed by reaction with oxygen, and atmospheric methane concentrations plummeted from perhaps 1,000 parts per million to just a few parts per million, triggering a catastrophic cooling that may have plunged the entire planet into a global glaciation. This event, sometimes called the Huronian glaciation, lasted from approximately 2.4 to 2.1 billion years ago and may have been the most severe ice age in Earth's history. Geological evidence suggests that glaciers extended from the poles to the equator, covering the continents in ice sheets kilometers thick and freezing the surface of the oceans. The planet became a snowball, its white surface reflecting sunlight back into space and reinforcing the cold in a feedback loop that seemed impossible to break. Yet volcanic activity continued beneath the ice, releasing carbon dioxide that could no longer be removed by weathering of silicate rocks, a process that requires liquid water and exposed rock surfaces. Over millions of years, carbon dioxide accumulated in the atmosphere until it reached concentrations perhaps 300 times higher than today, creating a greenhouse effect powerful enough to overcome the reflective cooling of the ice. The snowball melted rapidly once the threshold was crossed, perhaps in as little as a few thousand years, flooding the continents with meltwater and exposing bare rock to intense chemical weathering. The aftermath of the Huronian glaciation saw oxygen levels stabilize at their new, higher baseline, and life began to adapt to this transformed world. Some organisms evolved enzymes called superoxide dismutases and catalases that could neutralize the reactive oxygen species that formed inside their cells, converting these dangerous molecules into harmless water and oxygen gas. Others developed respiratory metabolisms that could harness the reactivity of oxygen to extract far more energy from organic compounds than fermentation alone could provide, oxidizing glucose completely to carbon dioxide and water, and capturing the released energy in molecules of ATP. This aerobic respiration yields approximately 18 times more energy per glucose molecule than anaerobic fermentation, a massive increase in metabolic efficiency that would eventually enable the evolution of large, active, multicellular organisms. But that development still lay more than 1 billion years in the future, waiting for oxygen levels to rise further during a second oxygenation event around 800 to 540 million years ago. In the meantime, the cyanobacteria continued their patient work, generation after generation, each cell splitting water molecules and releasing oxygen atoms, slowly filling the atmosphere with the gas that would make complex life possible. Those cyanobacteria, splitting water and releasing oxygen through countless generations, carried within them something even more fundamental than their photosynthetic machinery. Coiled within each cell, in molecules of DNA that would have been invisible to any observer, lay the instructions for building every protein, every membrane, every light-harvesting pigment that made their existence possible. And within that genetic code, errors were accumulating at a rate so slow and so steady that they would eventually provide scientists billions of years later with a clock more reliable than any mechanical timepiece ever constructed. The DNA molecule itself is remarkably stable, its double helix structure providing a kind of chemical redundancy that allows cells to detect and repair most damage. Each strand serves as a template for the other, so when one nucleotide is altered or lost, the complementary strand often provides the information needed to restore the original sequence. The enzymes responsible for this repair work with extraordinary precision, proofreading each newly copied strand and correcting mismatches with an accuracy that approaches 1 error per billion nucleotides copied. Yet even this remarkable fidelity is not perfect, and over the vast timescales of evolutionary history, those rare, uncorrected errors accumulate like grains of sand settling on a beach. In modern bacteria, the mutation rate has been measured at approximately 0.003 mutations per genome per generation, meaning that roughly 1 in every 300 bacterial cells carries a new genetic change that was not present in its parent. For organisms with larger genomes and longer generation times, the numbers shift accordingly. The human genome, with its 3 billion base pairs, accumulates roughly 60 to 70 new mutations per generation, most of them occurring during the formation of sperm cells in the father's testes, where the DNA replication machinery must copy the entire genome hundreds of times over a lifetime. Most of these mutations are neutral, occurring in regions of the genome that do not code for proteins or in positions within genes where the change does not alter the amino acid sequence of the resulting protein. The genetic code is redundant in this way, with multiple 3-letter codons specifying the same amino acid. A change from GCU to GCC, for instance, still codes for the amino acid alanine, and the protein produced functions identically to its predecessor. These silent mutations accumulate freely, neither helped nor hindered by natural selection, drifting through populations like leaves floating on a slow current. It is precisely this neutrality that makes molecular clocks possible. Because neutral mutations are not subject to the pruning effects of natural selection, they accumulate at a rate determined almost entirely by the mutation rate itself. If 2 species share a common ancestor, and if neutral mutations have been accumulating independently in both lineages since that ancestor lived, then the number of differences between their DNA sequences should be roughly proportional to the time since they diverged. The more differences, the longer ago the split occurred. The first molecular clock was proposed in 1962 by Emil Zuckerkandl and Linus Pauling, who noticed that the hemoglobin proteins of different species differed by amounts that seemed to correlate with their evolutionary distance. Humans and gorillas, close relatives who shared a common ancestor perhaps 7 to 10 million years ago, had hemoglobin sequences that differed by only a few amino acids. Humans and horses, whose lineages diverged roughly 80 million years ago when the ancestors of primates and the ancestors of hoofed mammals went their separate ways, showed many more differences. The relationship was not perfect, but it was striking enough to suggest that protein sequences might serve as a kind of evolutionary chronometer. Modern molecular clocks rely primarily on DNA sequences rather than proteins, and they have been calibrated using fossils whose ages are known from radiometric dating. The mitochondrial DNA of mammals, for instance, accumulates substitutions at a rate of approximately 1 to 2% per million years in many lineages. This means that two species whose mitochondrial genomes differ by 10% likely shared a common ancestor roughly 5 to 10 million years ago. The nuclear genome evolves more slowly, with rates varying depending on the specific gene and the organism in question. But typical estimates for mammals fall in the range of 0.1 to 0.5% divergence per million years for protein-coding genes. These rates are not constant across all genes or all lineages, and calibrating molecular clocks requires careful attention to the specific sequences being compared. Genes that are essential for survival tend to evolve more slowly because most mutations in them are harmful and are eliminated by natural selection. The genes encoding the ribosomal RNA molecules that form the core of the protein synthesis machinery, for instance, are so critical that they have remained nearly unchanged across billions of years of evolution. The ribosomal RNA of a modern bacterium differs from that of a human cell by only about 30%, despite the fact that the lineages leading to bacteria and eukaryotes diverged somewhere between 2 and 3 billion years ago. At the other extreme, genes involved in immune recognition or sexual selection often evolve rapidly because they are subject to strong selective pressures that favor novelty. The major histocompatibility complex genes in vertebrates, which encode proteins that present foreign molecules to the immune system, are among the most variable genes in the genome, with some alleles persisting in populations for tens of millions of years, because the diversity itself provides a selective advantage against parasites and pathogens. The molecular clock has been used to date countless evolutionary divergences that left no fossil record. The split between the ancestors of humans and chimpanzees, estimated at roughly 6 to 7 million years ago based on molecular data, was confirmed when fossils of early hominins like Sahelanthropus chadensis were discovered in Chad and dated to approximately 7 million years old. The divergence of the major animal phyla during the Cambrian explosion, long thought to have occurred in a geologically sudden burst around 540 million years ago, now appears to have been preceded by a long period of molecular divergence stretching back perhaps 700 to 800 million years, with the body plans we recognize in fossils representing only the latest chapter in a much longer story of genetic differentiation. Within the human lineage, molecular clocks have revealed patterns invisible to the fossil record. The mitochondrial DNA of all living humans traces back to a single woman who lived in Africa approximately 150,000 to 200,000 years ago, not because she was the only woman alive at that time, but because the mitochondrial lineages of all other women from that era eventually died out through the random process of genetic drift. The Y chromosome tells a similar story, pointing to a common male ancestor who lived roughly 200,000 to 300,000 years ago. These molecular ancestors were not a couple, and they were not the only humans of their time, but their genetic material happened to be the only lineage that survived the bottlenecks and expansions of human population history. The precision of molecular clocks depends on understanding the factors that influence mutation rates. Organisms with shorter generation times tend to accumulate mutations faster in absolute terms, because they copy their DNA more frequently. Bacteria, dividing every 20 minutes under optimal conditions, can accumulate in a single day the number of mutations that would take a human lineage thousands of years to acquire. Yet when measured per generation rather than per year, mutation rates are remarkably similar across the tree of life, suggesting that the fundamental chemistry of DNA replication and repair has been conserved since the earliest cells. Temperature affects mutation rates as well, with warmer environments generally accelerating the chemical reactions that cause DNA damage. Organisms living in tropical climates tend to show slightly faster molecular evolution than their relatives in temperate or polar regions, a pattern that complicates efforts to apply a single clock rate across all lineages. The metabolic rate of an organism also plays a role, with species that burn energy faster, generating more reactive oxygen species that can damage DNA and increase mutation rates. Despite these complications, molecular clocks have become an indispensable tool for reconstructing the history of life. They have revealed that the major groups of flowering plants diverged from one another during the Cretaceous period, roughly 100 to 130 million years ago, even though the earliest unambiguous flower fossils date to only about 130 million years ago. They have shown that the ancestors of modern birds survived the mass extinction that killed the non-avian dinosaurs 66 million years ago, then diversified rapidly in the aftermath, filling ecological niches left vacant by the vanished reptiles. The mutations that drive these clocks are not distributed evenly across the genome. Certain sequences, called hotspots, are particularly prone to error because of their chemical structure or their position relative to other genomic features. The denucleotide CpG, where a cytosine is followed by a guanine, is especially unstable in vertebrate genomes because the cytosine is often chemically modified by the addition of a methyl group. And this methylated cytosine has a tendency to spontaneously convert to thymine through a process called deamination. CpG sites mutate roughly 10 times faster than other positions in the genome, creating a kind of fast-ticking clock that can be used to date recent evolutionary events with greater precision. At the finest scale, molecular clocks can even track changes within a single human lifetime. The mutations that accumulate in cancer cells as they divide and proliferate follow predictable patterns, and by counting these mutations, researchers can estimate how long a tumor has been growing and how many cell divisions have occurred since the first cancerous transformation. The same principles that date the divergence of species separated by hundreds of millions of years can be applied to trace the genealogy of cells within a single body, revealing the hidden history written in every genome. Those mutations, accumulating silently in every lineage across billions of years, would be nothing more than random noise without a force to sort them, to preserve the beneficial and discard the harmful. That force operates with no intention, no foresight, no plan, Yet it has sculpted every living thing on Earth with a precision that rivals the most careful engineer. Natural selection works through a simple arithmetic. Organisms that survive and reproduce pass their genes to the next generation, while those that fail leave no descendants. Over thousands and millions of generations, this differential survival reshapes populations with inexorable patience. The mathematics of selection are deceptively straightforward. If a mutation increases an organism's chance of surviving to reproduce by even 1%, that advantage compounds across generations like interest in a savings account. A beneficial allele that confers a 1% fitness advantage will spread from a single copy to fixation in a population of 10,000 individuals in roughly 4,000 generations. For bacteria dividing every 20 minutes, this could happen in less than 60 days. For elephants with a generation time of 25 years, the same process would require 100,000 years. The clock of adaptation ticks at different speeds for different organisms, but the underlying mechanism remains identical. Consider the peppered moth, Biston betularia, whose story illustrates selection operating on a timescale humans can actually observe. Before the Industrial Revolution, the light-colored form of this moth dominated English populations, its pale wings providing camouflage against lichen-covered tree bark. Dark-colored variants existed, but remained rare, perhaps comprising less than 2% of the population. Then coal smoke began blackening the trees of industrial cities, killing the pale lichens and exposing dark bark beneath. By 1895 in Manchester, the dark form had risen to 98% of the population. The selection coefficient, the measure of how much better one form survives than another, was approximately 0.3, meaning dark moths were 30% more likely to survive each generation than light ones. When clean air legislation reduced pollution in the 20th century, the selection reversed, and light moths began their slow return to dominance. This example, dramatic as it is, represents selection operating at an unusually rapid pace. Most evolutionary change proceeds far more gradually, driven by selection coefficients so small they would be undetectable in any single generation. A mutation that improves metabolic efficiency by 0.1%, or increases cold tolerance by a fraction of a degree, or marginally enhances the ability to digest a particular food source. Such tiny advantages accumulate over geological time into the vast diversity of adaptations that characterize life on Earth. The bacterial enzyme beta-lactamase provides a window into selection at the molecular level. This protein, which breaks down penicillin and related antibiotics, has evolved independently in numerous bacterial lineages since antibiotics entered widespread use in the 1940s. Researchers have reconstructed the mutational pathways by which sensitive bacteria became resistant, finding that resistance typically emerges through a series of 5 to 7 mutations, each providing a small incremental benefit. The first mutation might reduce the antibiotic's binding affinity by 10%. The second might increase the enzyme's catalytic rate by 15%. Subsequent mutations fine-tune the protein's structure until it can destroy antibiotics thousands of times faster than the ancestral enzyme. Each step along this pathway was favored by selection, each mutation spreading through bacterial populations in hospitals and farms and sewage treatment plants around the world. The eye, often cited as an example of irreducible complexity, actually demonstrates how selection can build elaborate structures through countless small improvements. Computer simulations by Dan Erik Nielsen and Suzanne Pelger in 1994 showed that a flat patch of light-sensitive cells could evolve into a camera-type eye through a series of 1,829 steps, each representing a 1% improvement in visual acuity. At a conservative estimate of 0.005% change per generation, this transformation would require only 364,000 generations, less than 500,000 years for organisms with annual reproduction. The fossil record confirms this timeline. The Cambrian explosion, beginning approximately 538 million years ago, saw the rapid appearance of sophisticated eyes in trilobites, anomalocaridids, and early vertebrates, all evolving independently from simpler light-sensing organs. Selection operates not only on physical structures, but on behaviors, life histories, and reproductive strategies. The Pacific salmon that exhausts itself swimming upstream to spawn, dying immediately after reproduction, has been shaped by selection favoring organisms that invest everything in a single reproductive event. The oak tree that produces thousands of acorns each year for centuries represents the opposite strategy, spreading reproductive effort across a long lifespan. Neither approach is inherently superior. Each represents an optimization for particular ecological circumstances, honed by millions of generations of differential survival. The strength of selection varies enormously across different traits and environments. Traits directly affecting survival and reproduction, immune function, fertility, predator avoidance, experience strong selection and evolve relatively quickly. Traits expressed only late in life, after reproduction has largely concluded, experience weak selection and tend to deteriorate. This explains why aging exists at all. Mutations that cause harm only in old age are nearly invisible to selection, accumulating in genomes over evolutionary time. The maximum lifespan of a species reflects this balance between the strength of selection and the accumulation of late-acting deleterious mutations. Sexual selection adds another dimension to the evolutionary process, sometimes driving the elaboration of traits that seem to decrease survival. The peacock's tail, requiring enormous metabolic investment and making escape from predators more difficult, persists because peahens prefer males with larger, more elaborate displays. Mathematical models by Ronald Fisher in the 1930s showed how such preferences can become self-reinforcing. Females who prefer ornamented males produce sons who inherit the ornaments and daughters who inherit the preference, creating a feedback loop that can drive traits to seemingly absurd extremes. The tail feathers of the long-tailed widow bird, reaching 0.5 meter in length, represent selection pushed to the very edge of what survival permits. Stabilizing selection, often overlooked in favor of more dramatic directional change, may be the most common form of natural selection in nature. Human birth weight provides a classic example. Babies weighing between 3.2 and 3.6 kilograms have the highest survival rates, while both smaller and larger infants face elevated mortality. This creates selection against both extremes, maintaining the population mean at an optimal intermediate value. Such stabilizing selection can persist for millions of years, explaining why some organisms, horseshoe crabs, coelacanths, ginkgo trees, have remained morphologically similar across vast stretches of geological time. Stasis is not the absence of selection, but its consequence, a dynamic equilibrium maintained by constant pressure against deviation. The response to selection depends critically on the genetic variation available in a population. A population with abundant genetic diversity can adapt rapidly to new conditions. A population depleted of variation by inbreeding or bottlenecks may lack the raw material for evolutionary change. The cheetah, having passed through a severe population bottleneck approximately 10,000 years ago, possesses so little genetic variation that skin grafts between unrelated individuals are not rejected. Their immune systems cannot distinguish self from non-self. This genetic uniformity may limit the species' ability to adapt to future challenges, a vulnerability created by ancient demographic catastrophe. Selection acts on phenotypes, the observable characteristics of organisms, but its effects are recorded in genotypes, the underlying genetic sequences. This distinction matters because the relationship between genotype and phenotype is rarely simple. A single gene may influence multiple traits, a phenomenon called pleiotropy, meaning selection on one characteristic can produce correlated changes in others. The genes controlling body size in dogs also affect skull shape, leg length, and even temperament, which is why artificial selection for small size in breeds like Chihuahuas has produced a constellation of associated traits that breeders never directly selected. Across the vast expanse of evolutionary time, natural selection has transformed simple, self-replicating molecules into the staggering complexity of modern ecosystems. Each adaptation, from the antifreeze proteins of Arctic fish to the echolocation of bats to the photosynthetic machinery of plants, represents millions of generations of incremental refinement, countless small improvements preserved and accumulated by the simple arithmetic of differential reproduction. The process requires no designer, no plan, no foresight, only variation, inheritance, and the relentless filtering of survival. Yet that relentless filtering has not always proceeded at the same measured pace. 5 times in the past 540 million years, the steady accumulation of adaptations has been interrupted by catastrophic events that swept away the majority of species in geological instants. These mass extinctions, each one eliminating between 70 and 96% of all species on Earth, represent the great punctuation marks in the history of life. Moments when the patient work of natural selection was overwhelmed by forces operating on scales that no adaptation could anticipate or survive. The most severe of these catastrophes struck 252 million years ago, at the boundary between the Permian and Triassic periods. The Siberian Traps, a volcanic province covering an area larger than Western Europe, erupted continuously for roughly 1 million years, releasing an estimated 3 million cubic kilometers of basalt lava. But the lava itself was not the primary killer. The eruptions injected massive quantities of carbon dioxide and sulfur dioxide into the atmosphere, perhaps 40,000 gigatons of carbon over the course of the event. global temperatures rose by 8 to 10 degrees Celsius. Ocean temperatures in the tropics may have reached 40 degrees Celsius, hot enough to denature the proteins of most marine organisms. The warming triggered the release of methane hydrates from ocean sediments, amplifying the greenhouse effect in a feedback loop that pushed the planet toward conditions incompatible with complex life. The oceans became stratified and anoxic, their waters depleted of the oxygen that marine animals required. Hydrogen sulfide, produced by anaerobic bacteria thriving in the oxygen-free depths, bubbled up to poison surface waters and leak into the atmosphere, where it destroyed the ozone layer and bathed the land in ultraviolet radiation. The evidence lies in the rocks, a sharp spike in the ratio of carbon-12 to carbon-13, indicating a massive release of isotopically light carbon from volcanic emissions and decaying organic matter. Fungal spores become suddenly abundant in the fossil record, the signature of a world dominated by decay as forests died and rotted across entire continents. When the counting was done, 96% of all marine species had vanished. On land, 70% of terrestrial vertebrate species disappeared. The trilobites, those armored arthropods that had crawled across ocean floors for 300 million years, finally succumbed after surviving 4 previous extinction events. The great synapsid predators that had dominated Permian landscapes, animals like the saber-toothed gorgonops and the massive Inostrancevia, left no descendants. The recovery would take 10 million years, longer than any other extinction event, a span of time during which the Earth remained impoverished and strange. 66 million years ago, a different kind of catastrophe struck with far greater speed. An asteroid roughly 10 to 15 kilometers in diameter, traveling at approximately 20 kilometers per second, struck what is now the Yucatan Peninsula of Mexico. The impact released energy equivalent to 100 million megatons of TNT, roughly 1 billion times more powerful than the atomic bombs dropped on Hiroshima and Nagasaki combined. The asteroid punched through the Earth's crust in less than a second, excavating a crater 180 kilometers wide and 20 kilometers deep. The rock at the impact site, rich in sulfur-bearing minerals called evaporites, vaporized instantly, injecting billions of tons of sulfur dioxide and dust into the stratosphere. Within hours, ejecta from the impact rained down across the entire planet, heating the atmosphere to temperatures that may have ignited wildfires on a global scale. Soot from burning forests blocked sunlight for months, perhaps years. Photosynthesis collapsed. The sulfur dioxide combined with water vapor to form sulfuric acid aerosols that further blocked sunlight and fell as acid rain, devastating both terrestrial and marine ecosystems. Global temperatures dropped by as much as 26 degrees Celsius in the immediate aftermath, a nuclear winter triggered by rock rather than weapons. The evidence for this impact is written in a thin layer of clay found at the Cretaceous-Paleogene boundary in rock formations around the world. This layer contains iridium at concentrations 30 times higher than normal, iridium being rare in Earth's crust, but common in asteroids. It contains shocked quartz grains, minerals deformed by pressures that only occur in nuclear explosions or asteroid impacts. It contains tiny glass spherules called tektites, droplets of molten rock that solidified as they fell back through the atmosphere. And it marks the precise moment when the non-avian dinosaurs, after dominating terrestrial ecosystems for 165 million years, vanished from the fossil record. Yet the recovery from this extinction, though devastating, proceeded far more rapidly than the recovery from the Permian catastrophe. Within 300,000 years, a mere heartbeat in geological time, mammalian diversity had begun to rebound. Within 10 million years, the major orders of modern mammals had appeared, the ancestors of whales and bats and primates and rodents, radiating into ecological niches left vacant by the dinosaurs. This pattern of rapid recovery following the end Cretaceous extinction, compared to the prolonged desolation after the end Permian event, reveals something fundamental about the nature of mass extinctions. The speed and completeness of recovery depends not just on the severity of the extinction itself, but on the environmental conditions that persist afterward. The Permian extinction was caused by sustained environmental degradation lasting hundreds of thousands of years, and the volcanic activity continued to destabilize climate long after the initial crisis. The Cretaceous extinction, by contrast, was triggered by a single instantaneous event. Once the dust settled and the acid rain ceased, the fundamental conditions for life — sunlight, liquid water, stable temperatures — returned relatively quickly. The survivors found themselves in a world depleted of competitors, but otherwise hospitable, and evolution proceeded to fill the empty spaces with characteristic efficiency. The fossil record reveals a consistent pattern in these recoveries. In the immediate aftermath of each mass extinction, ecosystems are dominated by what paleontologists call disaster taxa, opportunistic species that thrive in disturbed environments. After the end Permian extinction, the early Triassic oceans were dominated by just a handful of species: the bivalve Chloria, the ammonoid Ophyxerus, and a few species of conodonts. These organisms appear in fossil assemblages across the entire world, their cosmopolitan distribution reflecting the collapse of the complex, regionally differentiated ecosystems that had existed before. Diversity was not merely reduced, it was homogenized. The recovery of biodiversity follows a predictable trajectory, though the timescales vary enormously. First, the surviving lineages expand to fill available ecological space, often evolving into forms quite different from their pre-extinction ancestors. The mammals that survived the end Cretaceous extinction were mostly small, nocturnal insectivores, but within 15 million years, their descendants included the first whales, Pachycetus, a wolf-sized creature that hunted fish in shallow Pakistani rivers 50 million years ago, whose ear bones already showed the modifications that would eventually allow its descendants to hear underwater. The transition from land-dwelling mammal to fully aquatic whale took approximately 15 million years, a pace of roughly one major anatomical modification every few million years. The recovery of marine ecosystems after the end Permian extinction illustrates the slow rebuilding of ecological complexity. Reef ecosystems, which had been dominated by rugose and tabulate corals before the extinction, did not recover for 10 million years. When reefs finally returned in the Middle Triassic, they were built by entirely different organisms, scleractinian corals, the ancestors of modern reef-building corals, which had been minor components of Permian ecosystems. The extinction had not merely reduced diversity, it had reshuffled the ecological deck, elevating previously marginal groups to dominance. This pattern of ecological replacement following mass extinctions has shaped the entire history of life on Earth. The dinosaurs themselves rose to dominance only after the end Triassic extinction, 201 million years ago, eliminated many of the archosaur competitors that had previously kept them in check. Before that extinction, dinosaurs had been relatively minor components of terrestrial ecosystems, overshadowed by crocodile-like crurotarsans and large amphibians. The extinction cleared the ecological stage, and the dinosaurs, perhaps by chance, perhaps through some subtle competitive advantage, expanded to fill the vacant niches. The mathematics of recovery reveals the deep structure of these events. Studies of marine invertebrate diversity show that following each mass extinction, the rate of speciation increases dramatically while the rate of extinction decreases. This pattern, called diversity-dependent diversification, reflects the abundance of empty ecological niches available to survivors. When competition is low and resources are abundant, new species can establish themselves more easily, and existing species face fewer pressures that might drive them to extinction. As diversity recovers and niches fill, the rate of speciation gradually slows while extinction rates rise until the system approaches a new equilibrium. The current rate of species extinction, estimated at 100 to 1,000 times the background rate that prevailed before human expansion, has led many scientists to suggest that we are witnessing the beginning of a sixth mass extinction. Whether this event will ultimately rival the Big Five in severity depends on factors that remain uncertain. The trajectory of climate change, the extent of habitat destruction, the success of conservation efforts. But the geological record offers a sobering perspective on timescales. Even if human-caused extinctions were to cease tomorrow, the recovery of biodiversity to pre-human levels would require millions of years, far longer than our species has existed, far longer than any human institution or memory could persist. The fossil record that documents those mass extinctions and their long recoveries also preserves something equally profound: the gradual emergence of the body architectures that define animal life today. For the first 3 billion years of Earth's history, life remained microscopic, single-celled, invisible to any eye that might have observed it. The transition from those simple cells to the complex multicellular organisms that would eventually fill every ecological niche on the planet unfolded across hundreds of millions of years, through a series of innovations so fundamental that they would constrain the forms of all animals that followed. The earliest multicellular organisms left traces so faint that scientists debated their nature for decades. In the Ediacaran period, named for the Ediacara Hills of South Australia where fossils were first discovered in 1946, strange impressions began appearing in rocks dating from approximately 635 to 538 million years ago. These organisms, Dickinsonia, Charnia, Kimberella, and dozens of others, bore little resemblance to any creature alive today. Dickinsonia, perhaps the most studied, grew as a flat, ribbed oval sometimes reaching over a meter in length yet possessed no mouth, no gut, no obvious means of locomotion. Chemical analysis of preserved organic molecules in 2018 revealed the presence of cholesteroids, steroids found almost exclusively in animals, finally confirming that these enigmatic forms were indeed our distant relatives rather than lichens, fungi, or failed experiments in multicellular organization. The Ediacaran organisms appear to have absorbed nutrients directly through their outer surfaces, a strategy that works only when the ratio of surface area to volume remains high. This constraint explains their peculiar shapes, flat, frond-like, quilted into segments that maximized the area available for absorption. They lacked the internal transport systems that would later allow animals to grow thick and active. Most seem to have lived as passive mat dwellers on the sea floor, perhaps grazing on bacterial films or simply absorbing dissolved organic matter from the water. Their world was one of stillness, of organisms that grew but did not chase, did not flee, did not compete in the ways that would later define animal existence. Then, approximately 538.8 million years ago, something changed. The boundary between the Ediacaran and Cambrian periods marks one of the most dramatic transitions in the history of life. Though the change itself unfolded across perhaps 20 million years, a duration that seems brief only against the immense backdrop of geological time. In rocks from this interval, paleontologists find the first evidence of active predation. Boreholes drilled through shells, bite marks on trilobite exoskeletons, the mineralized teeth of creatures designed to pierce and tear. The arms race between predator and prey had begun, and it would reshape the architecture of animal bodies forever. The Cambrian explosion, as this diversification is known, produced nearly all the major animal body plans, the phyla that exist today. Arthropods with their jointed exoskeletons, mollusks with their muscular feet and protective shells, chordates with their notochords and dorsal nerve cords, echinoderms with their five-fold symmetry and water vascular systems. The Burgess Shale of British Columbia, deposited approximately 508 million years ago, preserves this diversity in extraordinary detail. Anomalocaris, a meter-long predator with compound eyes containing 16,000 lenses, swept through the water column. Opabinia, with 5 eyes and a flexible proboscis, probed the sediment for prey. Hallucigenia, initially reconstructed upside down because its body plan seemed so alien, walked on paired legs beneath a row of protective spines. The genetic toolkit that enabled this explosion of form had been assembling for hundreds of millions of years before it was deployed. Hox genes, which specify the identity of body segments along the head-to-tail axis, appear to have originated in the common ancestor of all bilateral animals, perhaps 600 to 700 million years ago. These master regulatory genes act as switches, activating cascades of downstream genes that build specific structures, antennae here, legs there, wings in this segment, but not that one. The remarkable conservation of Hox genes across the animal kingdom, a fruit fly and a mouse use essentially the same genetic logic to pattern their bodies, reveals that the fundamental instructions for building complex body plans evolved once and have been modified ever since. The evolution of eyes illustrates how these genetic programs could be recruited and elaborated. The gene PAC6, which initiates eye development, is so ancient and so conserved that a mouse version can trigger eye formation in a fruit fly, despite the 500 million years separating these lineages. Yet the eyes themselves differ profoundly. The compound eyes of insects, the camera eyes of vertebrates, the mirror eyes of scallops all represent independent elaborations of a shared genetic starting point. The Cambrian fossil record captures this diversification in progress. Trilobites possessed compound eyes with calcite lenses, their crystalline structure preserved in such detail that paleontologists can calculate the visual acuity of creatures dead for 500 million years. The mineralization of skeletons, the development of hard parts from calcium carbonate, calcium phosphate, and silica, transformed both the fossil record and the ecology of the oceans. Before the Cambrian, most organisms left only trace fossils, the burrows and tracks of soft-bodied creatures. The evolution of shells and exoskeletons created both new defenses against predation and new surfaces for muscles to attach, enabling more powerful and precise movements. The chemistry of seawater played a role in this transition. Calcium ion concentrations in the late Precambrian oceans may have reached levels that made mineralization energetically favorable, or even necessary to prevent toxic accumulation within cells. The colonization of the seafloor's third dimension, the water column above the sediment, opened new ecological opportunities and new selective pressures. Swimming requires streamlined bodies, fins, or other control surfaces, and sensory systems capable of tracking prey or avoiding predators in three-dimensional space. The earliest chordates, soft-bodied creatures resembling the modern lancelet Branchiostoma, possessed a notochord, a flexible rod running the length of the body, that provided a structure against which muscles could pull, enabling the undulating swimming motion that would eventually carry their descendants onto land. The pace of morphological change during the Cambrian was not uniform. Molecular clock analyses suggest that the genetic divergences between major animal groups may have occurred tens of millions of years before those differences became visible in the fossil record. The explosion of visible diversity may represent not the origin of new body plans, but their ecological deployment, the moment when environmental conditions, perhaps rising oxygen levels or the evolution of predation, made it advantageous to grow large, to develop hard parts, to move actively through the water. Oxygen concentrations in the late Ediacaran and early Cambrian fluctuated significantly, with some estimates suggesting that atmospheric oxygen reached perhaps 10 to 15% of modern levels, enough to support the metabolic demands of active, muscular animals. The body plans established during this interval have proven remarkably stable. No new phyla have originated in the 500 million years since the Cambrian, though existing phyla have diversified into millions of species occupying every conceivable habitat. The constraints that channel animal form, the physics of movement through water and air, the chemistry of structural materials, the logic of developmental gene networks, appear to limit the range of viable architectures. Evolution explores the space of possible forms, but that space is not infinite. The same solutions arise repeatedly. Eyes have evolved independently at least 40 times, wings at least 4 times. The streamlined body shape of fast swimmers in sharks, ichthyosaurs, and dolphins lineages separated by hundreds of millions of years. Those convergent solutions, the repeated invention of eyes and wings and streamlined forms, emerge because physics imposes the same constraints everywhere on Earth. But geography creates a different kind of evolutionary pressure, one that separates rather than unifies. When continents drift apart, carrying their cargo of living organisms into isolation, evolution begins conducting parallel experiments across vast oceanic barriers that no land animal can cross. The mechanism is plate tectonics, that same slow engine that builds mountains and recycles ocean floors. The Atlantic Ocean, which now separates Africa from South America by nearly 5,000 kilometers at its narrowest point, did not exist 200 million years ago. The supercontinent Pangaea held all major land masses together, and organisms could walk, crawl, or slither from what would become Antarctica to what would become Alaska. When Pangaea began fragmenting around 175 million years ago, it split populations that had been continuous, creating isolated gene pools that would never again exchange genetic material. South America separated from Africa approximately 130 million years ago, though the final deep-water connection severed around 100 million years ago. At the time of separation, both continents harbored similar faunas: early mammals, diverse dinosaurs, freshwater fish, and the ancestors of many modern plant lineages. The Atlantic initially measured only tens of kilometers across, narrow enough that some organisms might have rafted between shores on floating vegetation. But the mid-Atlantic ridge continued spreading at roughly 2.5 centimeters per year, and within 10 million years, the ocean had widened to hundreds of kilometers. Within 50 million years, it exceeded 1,000 kilometers. The biological connection was severed absolutely. The consequences of this separation appear throughout the fossil record and in the distribution of living species. The lungfish family Lepidosirenidae now exists as two genera, Lepidosiren in South America and Protopterus in Africa. These fish share a common ancestor that swam in the rivers of Gondwana before the continents parted. Their DNA sequences have diverged steadily since separation, and molecular clock calculations place their last common ancestor at approximately 100 million years ago, matching the geological evidence for when deep water finally isolated the two land masses. Similar patterns appear in the caechlid fish of African and South American lakes, in the side-necked turtles of both continents, and the distribution of certain plant families. The southern beech trees of the genus Nothofagus grow today in South America, Australia, New Zealand, and New Guinea, a distribution that makes no sense on a static Earth, but traces perfectly the fragmentation of Gondwana. Pollen from Nothofagus appears in Antarctic sediments from 80 million years ago, when Antarctica still connected Australia to South America and supported temperate forests rather than ice sheets. Australia's separation from Antarctica, completed around 45 million years ago, created the most dramatic natural experiment in evolutionary isolation. When Australia drifted northward, it carried a fauna dominated by marsupial mammals, pouched creatures whose young are born at an extremely early developmental stage and complete their growth attached to a nipple, usually within a pouch. The placental mammals that would come to dominate most other continents never established themselves in Australia until humans arrived roughly 65,000 years ago, bringing dingoes around 4,000 years ago. In this isolation, marsupials radiated into ecological roles filled by placentals elsewhere. The thylacine, or Tasmanian tiger, evolved a body form nearly identical to wolves and dogs, despite sharing a common ancestor with them more than 160 million years ago. Its skull, teeth, and limb proportions converged so closely on the canid pattern that early anatomists struggled to distinguish thylacine skeletons from those of wolves. This convergence demonstrates how similar ecological pressures, hunting medium-sized prey in open woodland, channel evolution towards similar solutions regardless of ancestry. Australian marsupials produced mole-like forms that burrow through sandy soils, mouse-like forms that scurry through leaf litter, cat-like predators, and the unique radiation of kangaroos and wallabies, which have no placental equivalent. The koala occupies a niche similar to certain South American sloths, spending its life in trees and subsisting on low-nutrient foliage. The wombat fills a role comparable to groundhogs or badgers in other continents. Each represents an independent evolutionary solution to the same ecological problem. Madagascar presents an even more extreme case. This island separated from the Indian subcontinent approximately 88 million years ago, after India itself had broken from Madagascar and Africa around 130 million years ago. Madagascar's isolation predates the evolution of most modern mammal groups, yet it harbors lemurs, primates found nowhere else on Earth. The ancestors of lemurs apparently rafted to Madagascar from Africa sometime between 60 and 50 million years ago, crossing the Mozambique Channel when it measured perhaps 400 kilometers across. Ocean currents at the time may have favored westward transport, and a small founding population of primitive primates established themselves on the island. From that single colonization event, lemurs diversified into more than 100 species, occupying every available niche. The ii evolved an elongated middle finger to extract insect larvae from wood, filling the ecological role of woodpeckers, which never reached Madagascar. The Indri, largest of living lemurs at roughly 9 kilograms, browses on leaves in the forest canopy. The mouse lemurs, weighing as little as 30 grams, hunt insects and small vertebrates in the understory. Extinct giant lemurs, some weighing over 200 kilograms, filled niches comparable to gorillas and ground sloths before human arrival approximately 2,000 years ago. The tenrecs of Madagascar demonstrate similar radiation from a single ancestor. These small mammals, superficially resembling shrews and hedgehogs, colonized Madagascar around 30 million years ago. From one founding species, they evolved into more than 30 species, including aquatic forms, burrowing forms, and the hedgehog-like spiny tenrecs. Their diversity on a single island exceeds the diversity of their closest relatives across the entire African continent. New Zealand, isolated from other land masses for approximately 85 million years, took this pattern to its logical extreme. When New Zealand separated from Gondwana, it carried no land mammals, except possibly some early forms that later went extinct. In their absence, birds evolved to fill mammalian niches. The kiwi, a flightless bird with hair-like feathers and nostrils at the tip of its long bill, forages through leaf litter like a hedgehog or shrew. The kakapo, a flightless parrot weighing up to 4 kilograms, browses on vegetation like a rabbit. The moa, before human hunters drove them extinct around 600 years ago, included species standing 3.6 meters tall and weighing over 200 kilograms, filling the role of large browsing mammals. The geological record shows that these patterns of isolation and radiation have repeated throughout Earth's history. When Pangaea assembled from earlier continents around 335 million years ago, it brought together faunas that had evolved separately for hundreds of millions of years. The collision allowed species to spread across previously isolated land masses, triggering both extinctions as competitors met and opportunities as organisms encountered new environments. When Pangaea fragmented, the process reversed, creating new isolation and new opportunities for independent evolution. The Isthmus of Panama, rising from the sea approximately 3 million years ago, demonstrates how continental connections can reverse the effects of isolation. For most of the past 100 million years, South America remained an island continent, its fauna evolving in isolation much like Australia's. South American mammals included unique groups: the xenarthrans, ancestors of modern sloths, anteaters and armadillos; the notungulates, hoofed mammals that superficially resembled horses and rhinos but belonged to an entirely separate lineage; and the litopterns, including forms that evolved single-toed feet independently of true horses. When the Panamanian land bridge formed, North American mammals flooded southward while South American mammals moved north. The result, called the Great American Interchange, dramatically altered both faunas. North American predators, cats, bears, and dogs, largely replaced South American carnivorous marsupials. North American deer, tapirs, and relatives of camels established themselves throughout South America. Moving northward, armadillos, opossums, and porcupines successfully colonized North America, while ground sloths spread as far as Alaska before their extinction roughly 11,000 years ago. The interchange demonstrates that isolation does not create inherently superior or inferior faunas, but rather faunas adapted to particular conditions. Many South American lineages went extinct, not because they were poorly designed, but because they encountered competitors and predators against which they had no evolutionary experience. The notungulates and litopterns, successful for tens of millions of years, disappeared within a few million years of the interchange. Among those mammals that survived the Great Interchange, and among countless lineages before and since, a particular trend has repeated itself across evolutionary time: the gradual increase in brain size relative to body mass, a phenomenon scientists call encephalization. This is not a universal law of evolution, not an inevitable destination toward which all life strives, but rather a pattern that emerges when ecological circumstances favor the costly investment that nervous tissue demands. Brains are extraordinarily expensive organs. The human brain, weighing roughly 1.4 kilograms and comprising only about 2% of body mass, consumes approximately 20% of the body's metabolic energy at rest. Each gram of brain tissue requires roughly 20 times more energy than a gram of muscle tissue. This metabolic cost explains why encephalization is not universal. Many successful lineages have persisted for hundreds of millions of years with minimal neural investment. Crocodilians, essentially unchanged in body plan for over 80 million years, possess brains that represent only 0.05% of their body mass. Their ecological strategy, ambush predation in aquatic environments, simply does not reward the energetic expense of larger brains. The encephalization quotient, or EQ, provides a standardized measure for comparing brain sizes across species of different body masses. This ratio compares actual brain size to the expected brain size for an animal of that body mass, based on the general scaling relationship observed across mammals. An EQ of 1.0 represents the average. Values above indicate larger than expected brains. Modern humans possess an EQ of approximately 7.4 to 7.8, meaning our brains are nearly 8 times larger than expected for a mammal of our body size. Bottlenose dolphins reach EQs of roughly 4.1, chimpanzees approximately 2.2 to 2.5, and elephants about 1.3 to 2.0. The fossil record reveals that encephalization has proceeded independently in multiple mammalian lineages since the extinction of the non-avian dinosaurs 66 million years ago. Early Paleocene mammals, emerging into a world suddenly emptied of large reptilian competitors, possessed relatively small brains. Purgatorius, an early primate relative from roughly 65 million years ago, had a brain-to-body ratio typical of contemporary mammals, but far below that of modern primates. The subsequent 65 million years witnessed gradual increases in relative brain size across primates, vast cetaceans, elephants, and carnivores, each lineage following its own trajectory shaped by its particular ecological pressures. In the primate lineage leading to humans, the pace of encephalization has varied dramatically. For the first 50 million years of primate evolution, brain size increased slowly, roughly tracking the general mammalian trend. Egyptopithecus, a Catarrhine primate from the Egyptian Fayum deposits dating to approximately 29 million years ago, possessed a brain volume of roughly 30 cubic centimeters, comparable to modern howler monkeys of similar body size. The early hominoids that appeared around 20 million years ago showed modest increases, but nothing exceptional compared to other mammalian lineages. The acceleration began with the emergence of the genus Homo. Australopithecus afarensis, the species that includes the famous Lucy skeleton from 3.2 million years ago, possessed a brain volume of approximately 400 to 550 cubic centimeters, roughly equivalent to modern chimpanzees despite a smaller body size, yielding an EQ of perhaps 2.5. Homo habilis, appearing around 2.8 million years ago, showed brain volumes of 510 to 687 cubic centimeters. Homo erectus, emerging roughly 1.9 million years ago, ranged from 600 to 1,100 cubic centimeters across its long tenure, with later specimens approaching the lower range of modern human variation. The rate of increase during this period was remarkable by evolutionary standards. From Australopithecus to early Homo erectus, brain volume roughly doubled in less than 2 million years. From early Homo erectus to modern Homo sapiens, it nearly doubled again. This represents an average increase of approximately 150 cubic centimeters per million years in the later stages, extraordinarily rapid compared to the background rate of mammalian brain evolution, which typically proceeds at roughly 10 to 20 cubic centimeters per million years. Several hypotheses attempt to explain this acceleration. The social brain hypothesis proposes that the cognitive demands of living in complex social groups, tracking relationships, detecting cheaters, forming alliances, predicting others' behavior, created selection pressure for larger brains. Primate species living in larger social groups do tend to possess larger neocortices relative to the rest of the brain. The neocortex ratio, comparing neocortex volume to the volume of the rest of the brain, correlates strongly with average group size across primate species. Humans, with their neocortex comprising roughly 80% of total brain volume, fit predictions for a species with a natural group size of approximately 150 individuals, a number that appears repeatedly in human social organization, from hunter-gatherer bands to military units to corporate departments. The ecological intelligence hypothesis emphasizes the cognitive demands of extractive foraging, obtaining foods that require complex processing, such as nuts that must be cracked, tubers that must be dug and detoxified, or prey that must be tracked and captured. The expansion of African savannas beginning around 2.5 million years ago, driven by global cooling and drying trends, may have pushed hominin ancestors into ecological niches requiring more sophisticated foraging strategies. The archaeological record shows increasingly complex stone tools appearing in rough synchrony with brain expansion, from the simple older one choppers associated with Homo habilis to the symmetrical Acheulean hand axes of Homo erectus. The expensive tissue hypothesis addresses the metabolic problem directly. Brains require not only energy, but also specific nutrients, particularly long-chain polyunsaturated fatty acids like docosahexaenoic acid or DHA, which constitutes roughly 40% of the fatty acids in neuronal membranes. These nutrients are most abundant in animal tissues, particularly fish and shellfish. The hypothesis proposes that access to higher quality foods, especially meat and aquatic resources, relaxed the metabolic constraints on brain growth. Supporting this, the hominin gut appears to have shortened over evolutionary time. The human digestive tract is substantially smaller than expected for a primate of our body size, representing a metabolic savings that may have been redirected to neural tissue. The control of fire, with evidence dating back at least 1 million years, and possibly earlier, may have accelerated this process. Cooking breaks down plant cell walls and denatures proteins, dramatically increasing the caloric yield of foods. Raw foods require extensive chewing. Chimpanzees spend roughly 6 hours daily chewing their food, while humans average less than 1 hour. Cooking also detoxifies many plant compounds, expanding the range of edible foods. The energy savings from reduced gut size and reduced chewing time, combined with increased caloric extraction from cooked foods, may have provided the metabolic surplus necessary for continued brain expansion. The anatomical changes accompanying encephalization extend beyond brain size alone. The human skull has been extensively reorganized to accommodate a larger brain while maintaining the ability to pass through the birth canal. The human pelvis, adapted for bipedal locomotion, creates a birth canal significantly narrower than that of quadrupedal apes. This obstetric dilemma has been partially resolved by the birth of neurologically immature infants. Human babies are born with brains only about 25% of adult size, compared to roughly 40% in chimpanzees. The extended period of postnatal brain growth, continuing until approximately age 25, when the prefrontal cortex completes myelination, represents another distinctive feature of human development. The reorganization of brain structure has been as significant as the increase in size. The prefrontal cortex, involved in planning, decision-making, and impulse control, has expanded disproportionately in humans, comprising roughly 29% of the cortex, compared to approximately 17% in chimpanzees. Broca's area and Wernicke's area, regions associated with language production and comprehension, show distinctive organization in humans. The arcuate fasciculus, a bundle of nerve fibers connecting these language regions, is substantially larger and more developed in humans than in other primates. Yet intelligence, however measured, has emerged independently in multiple lineages. Corvids, crows, ravens, and jays possess brain-to-body ratios comparable to great apes, despite their small absolute brain size. New Caledonian crows manufacture and use tools, solve multi-step problems, and recognize individual human faces. Cetaceans, particularly dolphins and orcas, demonstrate complex social learning, cultural transmission of behaviors, and self-recognition in mirrors. Elephants show evidence of empathy, mourning behaviors, and the ability to cooperate in tasks requiring coordinated action. This convergent evolution of intelligence suggests that certain ecological conditions reliably favor cognitive investment: long lifespans that allow learning to accumulate, complex social structures that reward social cognition, and variable environments that reward behavioral flexibility over fixed instincts. The emergence of human-level intelligence may have been contingent on many factors aligning in a particular sequence, but the broader trend toward encephalization appears to be a recurring theme in the history of life, written independently in the neural tissue of primates, cetaceans, elephants, and birds across tens of millions of years. Those brains, shaped by millions of years of selection pressure in variable environments, would soon face the most dramatic environmental oscillations the planet had experienced since the Snowball Earth episodes of the Proterozoic. The same orbital mechanics that govern the Earth's path around the Sun would impose rhythmic pulses of cold and warmth, advancing and retreating ice sheets that would reshape continents, redirect ocean currents, and test the adaptability of every lineage that had evolved in the relatively stable warmth of the Cenozoic. The current Ice Age began approximately 34 million years ago, when Antarctica separated fully from South America and the circumpolar current established itself around the southern continent. That cold ring of water, flowing unimpeded around Antarctica at speeds averaging 4 kilometers per hour, thermally isolated the continent from warmer waters to the north. Ice sheets began accumulating, growing to thicknesses exceeding 4 kilometers in places, locking away water that would otherwise fill the oceans. But this Antarctic glaciation was merely the prelude to a more dramatic phase that would begin much later, when ice sheets spread across the northern hemisphere as well. Around 2.6 million years ago, the Isthmus of Panama completed its emergence from the sea, closing the gap between North and South America. This seemingly minor geological event, a land bridge perhaps 3 million years in the making, redirected ocean currents in ways that would transform global climate. The warm waters of the Atlantic, no longer able to flow directly into the Pacific, were deflected northward, carrying moisture that would fall as snow on the growing ice sheets of Greenland and northern Europe. The Quaternary glaciation had begun, and with it came the rhythmic advance and retreat of ice that would characterize the next 2.5 million years. These glacial cycles do not occur randomly. They follow patterns first calculated by the Serbian mathematician Milutin Milankovic in the early 20th century, patterns rooted in the gravitational interactions between Earth and the other bodies of the solar system. 3 orbital parameters combine to modulate the amount and distribution of solar energy reaching Earth's surface, and their overlapping cycles create the complex rhythm of ice ages and interglacials that the geological record preserves. The first parameter is eccentricity, the degree to which Earth's orbit deviates from a perfect circle. Currently, Earth's orbital eccentricity is approximately 0.017, meaning the planet's distance from the Sun varies by about 5 million kilometers over the course of a year. But this value is not constant. Gravitational tugs from Jupiter and Saturn stretch and compress Earth's orbit over cycles of roughly 100,000 and 400,000 years. When eccentricity is high, reaching values around 0.058, the difference between Earth's closest and farthest approach to the Sun becomes more pronounced, amplifying seasonal contrasts in one hemisphere while dampening them in the other. The second parameter is obliquity, the tilt of Earth's rotational axis relative to its orbital plane. This tilt, currently about 23.4 degrees, is what creates seasons. But the angle oscillates between 22.1 and 24.5 degrees over a cycle of approximately 41,000 years, pulled by the gravitational influence of the Moon and the Sun on Earth's equatorial bulge. When obliquity is high, summers receive more intense sunlight at high latitudes, and winters are correspondingly darker. When obliquity is low, the seasonal contrast diminishes, and summer sunlight at 65 degrees north latitude, the critical zone for ice sheet growth, becomes less intense. The third parameter is precession, the slow wobble of Earth's rotational axis, like a spinning top gradually tracing a circle in the sky. This wobble completes a full cycle every 26,000 years, but its climatic effect combines with the precession of Earth's orbital ellipse to produce a cycle of roughly 23,000 years. Precession determines which hemisphere experiences summer when Earth is closest to the Sun. Currently, the Northern Hemisphere's summer coincides with Earth's farthest point from the Sun, making northern summers relatively mild. 11,000 years ago, the configuration was reversed, and northern summers received significantly more solar energy. These 3 cycles, eccentricity, obliquity, and precession, combine like overlapping waves, sometimes reinforcing each other, sometimes cancelling out. The result is a complex but predictable pattern of variation in the solar energy received at high northern latitudes during summer. This summer insolation at 65 degrees north is the critical variable because it determines whether winter snow survives through the following summer or melts away. When summer insolation drops below a threshold of approximately 470 watts per square meter, snow begins to accumulate year after year, compacting into ice, spreading outward under its own weight. Ice sheets, once established, create powerful feedback loops that amplify the initial orbital forcing. Fresh snow reflects up to 90% of incoming sunlight back into space, compared to perhaps 10% for dark ocean water or forest. As ice spreads, more solar energy is rejected, cooling the planet further and allowing more ice to form. This albedo feedback can amplify a small orbital signal into a dramatic climate shift. The ice sheets that covered much of North America and northern Europe during glacial maxima reflected enough sunlight to reduce global average temperatures by approximately 4 to 7 degrees Celsius compared to interglacial conditions. The most recent glacial maximum occurred approximately 26,000 to 19,000 years ago. Ice sheets up to 3 kilometers thick covered Canada, extending as far south as present-day New York and Chicago. The Scandinavian ice sheet buried northern Europe under similar depths of ice. So much water was locked in these continental glaciers that global sea level dropped by approximately 120 meters, exposing vast continental shelves, connecting Britain to mainland Europe, and creating land bridges between Asia and North America across what is now the Bering Strait. The retreat of these ice sheets began around 19,000 years ago, driven by the increasing summer insolation that the Milankovitch cycles predicted. But the retreat was not smooth. Meltwater pulses released enormous volumes of fresh water into the oceans, sometimes disrupting the thermohaline circulation that distributes heat around the planet. The Younger Dryas cold snap, occurring between 12,900 and 11,700 years ago, saw temperatures in the North Atlantic region plunge back toward glacial conditions for over 1,000 years, possibly triggered by a massive release of meltwater from glacial Lake Agassiz into the North Atlantic. The ice cores extracted from Greenland and Antarctica preserve a detailed record of these oscillations, with atmospheric composition and temperature proxies recorded in annual layers of compressed snow. The ratio of oxygen 18 to oxygen 16 in the ice serves as a paleothermometer, revealing temperature swings of 10 to 15 degrees Celsius in Greenland, over timescales as short as decades during some transitions. Trapped air bubbles preserve samples of ancient atmosphere, showing that carbon dioxide concentrations dropped to around 180 parts per million during glacial maxima and rose to approximately 280 parts per million during interglacials, a feedback that amplified the orbital forcing through the greenhouse effect. The current interglacial, the Holocene, began approximately 11,700 years ago. Based on the Milankovitch cycles alone, the next glacial period would not be expected for another 50,000 years, as the current orbital configuration favors relatively stable, warm conditions. The climate stability of the Holocene, unusual in the context of the past million years, provided the backdrop against which agriculture emerged civilizations developed, and human populations expanded to their current numbers. The brains that evolved under the selective pressures of Pleistocene climate variability now contemplate a future in which their own activities may override the orbital rhythms that have governed ice ages for millions of years. Those orbital rhythms that have governed ice ages for millions of years have also orchestrated one of the most dramatic physical transformations visible on Earth's surface: the rise and fall of the global ocean. Sea level has never been static. It oscillates on timescales ranging from thousands to hundreds of millions of years, driven by the interplay of ice volume, ocean temperature, and the slow reshaping of the ocean basins themselves. The coastlines that seem so permanent on human maps are merely snapshots of a boundary that has wandered hundreds of kilometers inland and seaward across geological time. During the last glacial maximum, approximately 26,000 to 19,000 years ago, so much water was locked in continental ice sheets that global mean sea level stood roughly 125 meters lower than today. The Bering Land Bridge connected Asia to North America across what is now the Bering Strait, a crossing perhaps 1,500 kilometers wide at its maximum extent. The British Isles were not islands at all, but peninsulas attached to continental Europe across a now submerged landscape called Doggerland, where mammoths grazed and human hunters pursued their prey across river valleys that now lie beneath the North Sea. The Persian Gulf was a river valley. The Indonesian archipelago was largely connected, forming a landmass called Sunderland that extended the Asian continent thousands of kilometers to the southeast. Australia and New Guinea formed a single continent, Sahul, separated from Sunderland by narrow straits that early human migrants crossed, perhaps 65,000 years ago. The ice sheets that created these land bridges contained approximately 50 million cubic kilometers of frozen water, equivalent to roughly 3% of all the water in the modern ocean. As the Pleistocene gave way to the Holocene, this ice melted with varying speed. Between 14,700 and 14,200 years ago, a period called Meltwater Pulse 1A, sea level rose by approximately 16 to 25 meters in less than 500 years, a rate of roughly 40 millimeters per year, catastrophically fast by geological standards. Coastal communities, if any existed, would have witnessed the ocean advance inland by meters within a single human lifetime. The mechanisms behind such rapid pulses remain debated, but likely involved the collapse of ice sheets that had become unstable as warming oceans undercut their marine terminating margins. By approximately 7,000 years ago, the major ice sheets had largely completed their retreat, and sea level had risen to within a few meters of its present position. The rate of rise slowed dramatically, averaging less than 1 millimeter per year for most of the past 6 millennia. This relative stability allowed the formation of modern deltas, barrier islands, and coastal wetlands, features that require thousands of years of steady conditions to develop. The Nile Delta, the Ganges-Brahmaputra Delta, the Mississippi Delta, all are products of this Holocene stillstand, accumulating sediment at coastlines that remained approximately fixed long enough for rivers to build their characteristic fan-shaped deposits. But the Pleistocene oscillations, dramatic as they were, represent only the most recent chapter in a much longer history of sea level change. The geological record preserves evidence of far greater variations, driven not by ice sheets alone, but by the fundamental geometry of the ocean basins. The volume of the ocean basins depends on the configuration of mid-ocean ridges, the spreading rate of tectonic plates, and the total area of continental crust. When mid-ocean ridges spread rapidly, they are hotter and more buoyant, displacing more water and causing sea level to rise even without any change in the total amount of water on Earth. When spreading slows, ridges cool and subside, deepening the basins and causing sea level to fall. During the Cretaceous period, between approximately 145 and 66 million years ago, sea level stood perhaps 200 to 270 meters higher than today. This was not primarily because of absent ice sheets, though the Cretaceous was indeed a greenhouse world with little or no permanent ice. The primary cause was the configuration of the ocean basins themselves. The supercontinent Pangaea had recently fragmented, and new ocean basins were forming between the separating continents. Young, hot mid-ocean ridges occupied vast volumes that would later subside as the ocean floor aged and cooled. The Atlantic Ocean was narrow and young, its ridge system displacing water onto the continental margins. The result was a world in which shallow seas flooded the continental interiors, to an extent not seen before or since. The Western Interior Seaway split North America in two, stretching from the Gulf of Mexico to the Arctic Ocean, a shallow marine corridor perhaps 1,000 kilometers wide at its maximum extent. Much of Europe was submerged beneath the Tethys Sea and its extensions. The chalk deposits of the White Cliffs of Dover, the limestone formations of the Texas Hill Country, the vast chalk beds of Kansas that yield mosasaur and plesiosaur fossils, all accumulated as marine sediments on flooded continental shelves during this high stand interval. The organisms that lived in these shallow seas left behind not only fossils, but also chemical signatures that allowed geologists to reconstruct ancient sea levels with surprising precision. The ratio of oxygen isotopes in the calcium carbonate shells of marine organisms reflects both the temperature of the water in which they grew and the total volume of ice on Earth. Oxygen-18, the heavier stable isotope, is preferentially left behind when water evaporates, and it accumulates in the ocean when ice sheets grow and sequester the lighter oxygen-16 on land. By measuring oxygen isotope ratios in foraminifera shells extracted from deep-sea sediment cores, scientists have reconstructed a continuous record of ice volume and sea level extending back tens of millions of years. This record reveals that the current pattern of glacial-interglacial cycles, with their 100-meter sea level swings, is geologically unusual. For most of the past 500 million years, Earth has been warmer than today, with little or no permanent ice at the poles. The transition to the current icehouse state began approximately 34 million years ago, when the Antarctic ice sheet first formed, as Antarctica became isolated over the South Pole, and the circumpolar current established thermal isolation of the southern continent. Sea level dropped by approximately 55 meters as water was transferred from ocean to ice. The northern hemisphere remained largely ice-free until approximately 2.7 million years ago, when the Isthmus of Panama closed and altered ocean circulation patterns, triggering the Pleistocene ice ages and their characteristic sea level oscillations. The rate of sea level change matters as much as its magnitude. Coral reefs, which require sunlight and thus grow only in shallow water, can keep pace with sea level rise of approximately 10 millimeters per year by growing upward. Faster rates drown the reefs, leaving them stranded in water too deep for photosynthesis. The geological record contains numerous drowned reefs, their growth terminated by rapid transgressions that outpaced their ability to build upward. Conversely, slow sea level fall exposes reefs to air, killing the living coral and leaving behind limestone terraces that mark former sea levels, like bathtub rings around an island. These terraces provide some of the clearest evidence for past sea level positions. The raised coral terraces of Barbados, Huon Peninsula in Papua New Guinea, and the Red Sea coast preserve a staircase of former shorelines, each representing an interglacial high stand when sea level briefly matched or exceeded modern levels. Uranium-thorium dating of the coral in these terraces yields precise ages, allowing correlation with the orbital cycles that drove the glacial-interglacial rhythm. The highest terrace on Barbados, dating to approximately 400,000 years ago, stands roughly 20 meters above modern sea level, suggesting that during some past interglacials, sea level was significantly higher than today, implying smaller ice sheets than currently exist in Greenland and Antarctica. The sediments that accumulate along coastlines also record the patient oscillation of the sea. Sequence stratigraphy, a discipline that emerged at the late 20th century, interprets the vertical stacking of sedimentary layers in terms of sea level cycles. When sea level rises, coastlines migrate landward in a process called transgression, and fine-grained sediments accumulate in deepening water. When sea level falls, coastlines migrate seaward in regression, and coarser sediments prograde over the former marine deposits. The resulting packages of sediment, bounded by surfaces that represent periods of erosion or non-deposition, can be traced across entire continental margins and correlated globally, revealing sea level cycles operating on timescales of millions of years. The longest of these cycles, called first-order cycles, span 200 to 400 million years and reflect the assembly and breakup of supercontinents. When continents cluster together, as during Pangaea, the total length of mid-ocean ridges is minimized, ocean basins are deep, and sea level is low. When continents disperse, new ridges form, basins shallow, and sea level rises. Superimposed on these are second-order cycles of 10 to 100 million years, driven by changes in spreading rates and the subduction of old, cold oceanic lithosphere. Third-order cycles of 1 to 10 million years may reflect smaller tectonic adjustments or the growth and decay of ice sheets during icehouse intervals. The current rate of sea level rise, measured by tide gauges and satellite altimetry, averages approximately 3.4 millimeters per year, more than 3 times the average rate of the past several thousand years. This acceleration reflects the thermal expansion of warming ocean water and the accelerating loss of ice from glaciers, Greenland, and Antarctica. The ocean absorbs more than 90% of the excess heat trapped by anthropogenic greenhouse gases, and water expands as it warms. A warming of 1 degree Celsius throughout the upper ocean causes roughly 100 millimeters of sea level rise from thermal expansion alone, independent of any ice melt. The ice sheets respond more slowly, but contain far more potential sea level rise. The Greenland ice sheet holds approximately 7.4 meters of sea level equivalent. The West Antarctic ice sheet, approximately 3.3 meters. The East Antarctic ice sheet, approximately 53 meters. Complete melting of all land ice would raise sea level by approximately 66 meters, submerging most coastal cities and reshaping the geography of every continent. Such complete deglaciation last occurred during the Eocene, more than 34 million years ago, and would require warming sustained over millennia. But even partial loss of ice sheets commits the planet to sea level rise that will continue for centuries after temperatures stabilize, as the massive ice bodies respond sluggishly to changed conditions. The coastlines of the future, like those of the past, will be determined by the balance between the water locked in ice and the water held in ocean basins whose geometry changes on timescales of tens of millions of years. The current configuration is a snapshot, a momentary position of a boundary that has wandered across continental shelves throughout Earth's history, flooding and exposing landscapes, isolating and connecting populations, reshaping the geography of life itself. That wandering boundary between land and sea has witnessed another transformation unfolding across the rocks it alternately covers and exposes: the slow, relentless chemical conversation between Earth's atmosphere and its solid surface. Every mineral exposed to air and water begins a journey of transformation, a patient dismantling at the molecular level that has been reshaping the planet's face for billions of years. The process begins with the simplest of reactions. When iron meets oxygen in the presence of water, electrons transfer from metal to gas, creating iron oxide, rust. This reaction proceeds at rates measured in micrometers per year under ordinary conditions. Yet, given geological time, it has painted entire landscapes red. The iron-rich rocks of Australia's Pilbara region, the rust-colored deserts of Mars, the banded iron formations that record Earth's oxygenation event, all testify to this fundamental chemical affinity between iron and oxygen. The chemistry of oxidation extends far beyond iron. Sulfide minerals like pyrite, iron disulfide, react with oxygen and water to produce sulfuric acid and iron hydroxides. This reaction generates heat and acidity, accelerating the breakdown of surrounding rocks. In coal mines and ore deposits, pyrite oxidation creates acid mine drainage with pH values as low as 2, more acidic than vinegar, that can persist for centuries after mining ceases. The reaction rate doubles with every 10 degrees Celsius increase in temperature, making tropical weathering far more aggressive than polar weathering. Silicate minerals, which compose more than 90% of Earth's crust, undergo a different kind of chemical transformation. When carbon dioxide dissolves in rainwater, it forms carbonic acid with a pH around 5.6, weak but persistent. This mild acid attacks feldspars, the most abundant mineral family in continental crust, breaking aluminum-silicon-oxygen bonds and releasing calcium, sodium, and potassium ions into solution. A single feldspar crystal might take 10,000 years to dissolve completely under temperate conditions. But across a landscape of exposed granite, this process removes material equivalent to lowering the surface by roughly 30 meters every million years. The products of silicate weathering carry profound consequences for Earth's climate. When calcium ions released from feldspar reach the ocean, they combine with dissolved carbon dioxide to form calcium carbonate, limestone. This reaction permanently removes carbon dioxide from the atmosphere, locking it into rock that may persist for hundreds of millions of years. The weathering of silicate rocks thus acts as Earth's long-term thermostat, a negative feedback loop that has helped maintain habitable temperatures across billions of years, despite the sun's gradually increasing luminosity. Clay minerals form as intermediate products of this weathering cascade. Kaolinite, montmorillonite, elite. These layered aluminosilicates represent partially dissolved feldspars, their crystal structures reorganized into flat sheets that can absorb water and swell. A gram of montmorillonite clay contains surface area equivalent to a basketball court, providing vast reaction surfaces for further chemical processes. These clays accumulate in soils, river deltas, and ocean floors, eventually lithifying into shales that comprise roughly 70% of all sedimentary rock. The rate of chemical weathering depends on temperature, rainfall, biological activity, and the composition of the parent rock. Basalt weathers roughly 10 times faster than granite under identical conditions because its minerals crystallized at higher temperatures and are therefore less stable at Earth's surface. Tropical rainforests, with their warm temperatures, abundant rainfall, and intense biological activity, weather rock perhaps 50 times faster than cold deserts. The Amazon basin alone accounts for roughly 12% of global silicate weathering, despite covering less than 5% of Earth's land surface. Biological processes accelerate weathering in ways that purely chemical reactions cannot match. Plant roots secrete organic acids that dissolve minerals while physically prying apart rock along fractures. Lichens, those symbiotic partnerships between fungi and algae, colonize bare rock surfaces and extract nutrients by dissolving the substrate beneath them. Bacteria in soil oxidize iron and sulfur compounds, generating acids that attack surrounding minerals. The evolution of land plants roughly 450 million years ago may have increased weathering rates by a factor of 10, drawing down atmospheric carbon dioxide and contributing to the glaciations of the late Paleozoic. Oxygen itself has not always been available for these reactions. For the first 2 billion years of Earth's history, the atmosphere contained less than 1 part per million of free oxygen, a trace gas produced by photosynthetic bacteria but immediately consumed by reduced minerals at the surface. Iron dissolved in ancient oceans, sulfur gases vented from volcanoes, and organic matter from dead cells all scavenged oxygen as fast as life produced it. The planet's surface remained chemically reduced, its iron locked in greenish ferrous minerals rather than the rusty ferric compounds that dominate today. The Great Oxygenation Event, roughly 2.4 billion years ago, marked the moment when oxygen production finally exceeded the capacity of surface sinks to absorb it. Atmospheric oxygen rose to perhaps 1 or 2% of modern levels. triggering the most extensive oxidation event in Earth's history. The banded iron formations that had accumulated for hundreds of millions of years ceased forming as dissolved iron precipitated out of the oceans. Continental surfaces began their long transformation from gray and green to the reds and browns that characterize oxidized landscapes. This oxidation continues today, though the most easily oxidized materials have long since reacted. Fresh rock exposed by erosion, volcanic eruptions, or tectonic uplift immediately begins its chemical transformation. A newly fractured granite surface will develop a weathering rind, a discolored outer layer of altered minerals that thickens at rates of roughly 1 to 10 micrometers per year depending on climate. After 1 million years, this rind might extend several centimeters into the rock, its original feldspars converted to clays, its iron-bearing minerals stained with rust. The chemistry of weathering creates distinctive landscapes. Limestone dissolves readily in carbonic acid, producing karst topography, sinkholes, caves, and underground rivers that riddle soluble bedrock. The dissolution rate of limestone averages roughly 50 millimeters per 1,000 years in temperate climates, fast enough to carve extensive cave systems within a few million years. Mammoth Cave in Kentucky extends more than 650 kilometers through Mississippian-age limestone, dissolved by groundwater over the past 10 million years. Granite weathers differently, its constituent minerals dissolving at different rates. Quartz resists chemical attack and accumulates as sand while feldspars dissolve into clays. The result is the distinctive rounded boulders of granite landscapes, their corners and edges preferentially weathered where water can attack from multiple directions. These core stones, surrounded by decomposed granite called grus, characterize tropical granite terrains from Brazil to Zimbabwe. The oxidation of organic matter represents another dimension of planetary weathering. Dead organisms contain reduced carbon compounds that react with atmospheric oxygen, releasing carbon dioxide and completing the cycle that photosynthesis began. Most organic matter oxidizes within years or decades, but some escapes into sediments where oxygen cannot reach it. This buried carbon, accumulating over hundreds of millions of years, became the coal, oil, and natural gas that industrial civilization now returns to the atmosphere in geological instants. Human activities have accelerated oxidation in ways unprecedented in Earth's history. The burning of fossil fuels releases carbon that took millions of years to accumulate, oxidizing it within centuries. Mining exposes sulfide minerals to air and water, generating acid drainage that persists for generations. Agriculture strips vegetation that would otherwise protect soil from oxidation, allowing organic matter to decompose and erode. The current rate of carbon release exceeds any natural process in the geological record, including the volcanic outgassing that triggered past mass extinctions. Yet even at this accelerated pace, the fundamental chemistry remains unchanged. Oxygen still seeks electrons from reduced compounds. Water still carries acids that dissolve minerals. The patient transformation of rock to soil to sediment to rock continues as it has for billions of years, indifferent to the brief acceleration imposed by one species on one planet. The rust spreading across an abandoned bridge follows the same chemical pathways as the oxidation of ancient iron formations. The limestone dissolving beneath a modern city obeys the same equilibrium constants that governed Paleozoic seas. Those chemical pathways, the oxidation of iron, the dissolution of limestone, the weathering of silicates, all share a deeper unity that transcends their specific reactions. Each represents a system moving toward greater disorder, releasing energy that disperses into the environment, transforming concentrated structures into scattered particles. This tendency governs not just chemistry, but every process in the universe, from the cooling of stars to the mixing of ocean currents to the decay of radioactive nuclei. Physicists call it the second law of thermodynamics, and it provides the arrow that gives time its direction. The concept emerges from a deceptively simple observation. Heat flows spontaneously from hot objects to cold ones, never the reverse. A cup of coffee cooling on a table releases thermal energy into the surrounding air, and that energy spreads outward, warming the room by an imperceptible fraction of a degree. The total energy remains constant. The first law of thermodynamics guarantees this conservation, but the energy becomes less concentrated, less available for doing work. The Austrian physicist Ludwig Boltzmann quantified this tendency in the 1870s, connecting the macroscopic flow of heat to the microscopic behavior of atoms and molecules. Boltzmann's insight was statistical. A hot object contains molecules moving at high average speeds, while a cold object contains molecules moving more slowly. When these objects touch, fast molecules collide with slow ones, transferring kinetic energy through countless random interactions. The overwhelming probability favors energy spreading from the concentrated source to the dispersed surroundings, simply because there are vastly more ways for energy to be spread out than concentrated. The number of possible arrangements, the entropy, increases as systems evolve toward their most probable configurations. Consider a deck of cards fresh from the factory, arranged in perfect order by suit and rank. Shuffle it once and some order remains. Shuffle it 1,000 times, and the arrangement becomes essentially random, one of approximately 8 times 10 to the 67th possible orderings. The probability of returning to the original sequence through random shuffling is so vanishingly small, about 1 in 10 to the 68th, that it would never occur in the lifetime of the universe. Yet no physical law forbids it. The arrow of time emerges not from impossibility, but from overwhelming improbability. This statistical foundation explains why entropy increase appears absolute despite being probabilistic. A kilogram of ice at 0 degrees Celsius contains roughly 3 times 10 to the 25th water molecules. The probability that all these molecules would spontaneously concentrate their thermal energy into a small region, causing part of the ice to heat while the rest cools further, is so astronomically small that it would not occur once in 10 to the 10 billionth years. For all practical purposes, the second law is inviolable, even though it rests on probability rather than absolute prohibition. The entropy of an isolated system can only increase or remain constant, never decrease. But Earth is not an isolated system. Solar radiation pours onto the planet at a rate of approximately 1,361 watts per square meter, delivering concentrated energy in the form of visible light photons with temperatures around 5,800 Kelvin. The planet radiates this energy back into space as infrared photons at roughly 255 Kelvin. The total energy entering and leaving remains balanced, but the entropy exported exceeds the entropy imported. Each high-energy visible photon carries less entropy than the 20 or so low-energy infrared photons that carry away the same total energy. This entropy gradient allows Earth to maintain complex, ordered structures, crystals, organisms, ecosystems, while the universe as a whole continues its march toward disorder. Living systems exploit this gradient with remarkable efficiency. A single cell maintains chemical concentrations thousands of times different from its surroundings, pumping ions against their gradients, synthesizing complex molecules from simple precursors, replicating its genetic information with error rates below 1 in a billion base pairs. All of this apparent order creation is paid for by entropy increases elsewhere, the heat released by metabolism, the disordered waste products excreted, the infrared radiation ultimately emitted to space. A human body at rest generates approximately 80 watts of thermal power, enough to raise the entropy of the environment by roughly 0.27 joules per Kelvin per second. The same accounting applies to every ordered structure on Earth. A growing crystal of quartz decreases local entropy as silicon and oxygen atoms arrange themselves into precise tetrahedral lattices, but the heat released during crystallization, the enthalpy of formation, increases the entropy of the surrounding rock and water by a greater amount. A river delta building outward into the sea creates intricate branching patterns, but the gravitational potential energy released as sediment settles drives turbulent mixing that disperses heat and dissolved chemicals. The total entropy of the universe increases with every crystal formed, every delta extended, every organism born. Geological processes operate within these thermodynamic constraints across timescales spanning billions of years. The differentiation of the early Earth, heavy iron sinking to form the core while lighter silicates rose to form the mantle, released gravitational potential energy equivalent to approximately 10 to the 32nd joules, enough to raise the planet's temperature by thousands of degrees. This heat has been slowly radiating into space ever since, driving mantle convection, plate tectonics, and volcanic activity. The current rate of heat loss from Earth's interior averages about 0.09 watts per square meter, totaling roughly 47 terawatts globally. At this rate, the planet will require billions of years to cool to thermal equilibrium with space. Radioactive decay contributes significantly to this internal heat budget. Uranium-238, with its half-life of 4.47 billion years, still releases energy as it transforms through a chain of 14 decay steps into stable lead-206. Each decay event converts a tiny amount of mass into kinetic energy of the emitted particles, following Einstein's equivalence of mass and energy. The total radioactive heat production within Earth currently amounts to roughly 20 terawatts, about half the total heat flow. 4 billion years ago, when radioactive isotopes were more abundant, this contribution was several times larger, driving more vigorous convection and faster plate motions. The cooling of Earth represents entropy increase on a planetary scale. Concentrated thermal energy in the core and mantle gradually disperses into the cold vacuum of space, where the cosmic microwave background radiation maintains a temperature of just 2.73 Kelvin. The temperature gradient between Earth's interior at roughly 5,400 Kelvin and this cosmic cold sink provides the thermodynamic driving force for all geological activity. When this gradient eventually diminishes, in perhaps 10 billion years, plate tectonics will cease, volcanic activity will end, and the planet will become geologically dead, like Mars today. Stars follow the same thermodynamic trajectory on larger scales and longer timescales. The Sun converts approximately 600 million tons of hydrogen into helium every second, releasing energy through nuclear fusion at a rate of 3.8 times 10 to the 26th watts. This energy flows outward from the core at 15 million Kelvin to the surface at 5,800 Kelvin, then radiates into space as photons that carry entropy away from the star. The Sun has been performing this conversion for 4.6 billion years and will continue for another 5 billion, gradually exhausting its hydrogen fuel and evolving toward a red giant phase before shedding its outer layers and cooling as a white dwarf over trillions of years. The ultimate fate of all stars follows this pattern of entropy increase. Massive stars burn through their fuel in mere millions of years, ending in supernova explosions that scatter heavy elements across interstellar space. These explosions represent enormous entropy increases, converting the concentrated gravitational and nuclear energy of a star into expanding shells of hot gas, radiation, and cosmic rays. The remnants, neutron stars or black holes, continue radiating energy, though at diminishing rates. Even black holes, once thought to be perfect entropy sinks, emit Hawking radiation at temperatures inversely proportional to their mass, slowly evaporating over timescales that dwarf the current age of the universe. The cosmic microwave background itself records the entropy state of the universe approximately 380,000 years after the Big Bang, when the plasma of the early universe cooled enough for electrons to combine with protons, allowing photons to travel freely for the first time. Those photons have been redshifted by the expansion of space, stretched from visible light to microwave frequencies, their temperature dropping from roughly 3,000 Kelvin to today's 2.73 Kelvin. The remarkable uniformity of this radiation, temperature variations of only about 1 part in 100,000, reflects the low entropy initial state from which all subsequent structure emerged. That initial low entropy presents a profound puzzle. The second law explains why entropy increases, but not why it was low to begin with. The smooth, hot, dense state of the early universe contained far less entropy than the same matter and energy would contain if collapsed into black holes, which represent the highest entropy configurations possible for a given mass. The gravitational clumping that formed galaxies, stars, and planets actually increased entropy, even as it created apparently ordered structures. The universe began in a special, improbable state, and everything since, every star, every planet, every living cell, has been a consequence of the long slide toward equilibrium. This slide continues in the present moment, in every process unfolding across the cosmos. The rust spreading on an abandoned bridge, the heat escaping from a cooling cup of coffee, the radioactive decay of atoms in granite bedrock, the infrared radiation streaming from Earth into space. all represent the same fundamental tendency: the dispersal of energy, the increase of entropy, the arrow that distinguishes past from future. Time flows in the direction of increasing disorder, and every transformation in the universe, from the grandest supernova to the smallest chemical reaction, marks another step along this irreversible path toward the distant equilibrium that physicists call heat death, when all gradients have dissipated and no further change is possible, and the universe rests at last in maximum entropy, silent and still across the infinite reaches of space and time.